Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the story of interstellar visitors and the quiet revolution they've brought to our understanding of the cosmos. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On October 19th, 2017, a telescope perched high on Haleakala catches something unusual moving against the stars. The Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, conducts its nightly sweep of the Hawaiian sky, searching for asteroids that might threaten Earth. Instead, it discovers something far more extraordinary: humanity's first confirmed visitor from the depths of interstellar space. The object travels too fast for an asteroid, follows the wrong path for a comet, and appears to come from somewhere beyond the gravitational embrace of our Sun. Its motion traces a hyperbolic arc through the inner solar system, the mathematical signature of something unbound by solar gravity. Within hours of discovery, astronomers realize they observe not a native of our cosmic neighborhood, but a true alien, a fragment of matter that formed around another star. They name it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first. The designation carries poetry and precision in equal measure, honoring both the location of discovery and the profound nature of the find. This wanderer represents the first confirmed interstellar object to visit our solar system, though scientists suspect countless others have passed unnoticed through the centuries when telescopes lack the sensitivity to detect such fleeting visitors. The object tumbles end over end as it races through the inner solar system, its brightness fluctuating in a precise rhythm every 7 hours and 20 minutes. These variations reveal something extraordinary about its shape. Oumuamua stretches at least 10 times longer than it is wide, perhaps 400 meters in length, but only 40 meters across. No known asteroid or comet in our solar system displays such extreme proportions. It resembles a cosmic cigar, or perhaps a needle of dark stone carved by forces humanity has never directly observed. The elongated form puzzles scientists. Conventional wisdom suggests that rotating objects should be roughly spherical due to their own gravity, or at least moderately flattened like spinning planets. Yet, Oumuamua maintains its needle-like proportions despite tumbling through space for potentially millions of years. Either it formed through some exotic process unknown in our solar system, or it represents a fragment of a much larger body that somehow retained its unusual dimensions after breaking away from its parent. Telescopes around the world turn toward this wanderer, capturing what little reflected sunlight bounces from its surface. The spectrum reveals a reddish coloration, similar to objects in the outer reaches of our own solar system, surfaces painted by billions of years of cosmic radiation. Yet, Oumuamua carries this patina from journeys between the stars, where temperatures hover just above absolute zero and charged particles stream from distant suns across the void. As observers calculate its trajectory, they realize this visitor follows a hyperbolic path, entering our solar system at 26 kilometers per second relative to the Sun. Such velocity cannot arise from gravitational interaction with any known planet or star in our immediate neighborhood. Oumuamua arrives from the direction of the constellation Lyra, though its journey likely began millions of years ago when that region of space held different stars in different positions. The galaxy rotates slowly, carrying star systems along orbital paths that scramble the ancient geography of the cosmos. The object's surface remains remarkably dark, reflecting only 4% of the sunlight that touches it, darker than charcoal, darker than most asteroids, darker even than volcanic glass. This suggests either a composition rich in organic compounds or a surface transformed by eons of interstellar weathering. Perhaps both processes have worked upon this visitor, cosmic radiation slowly altering whatever materials composed its original form while organic molecules accumulated like soot upon its ancient flanks. Scientists wonder what forces shaped such an unusual object. Did it fragment from a larger body during planetary formation around another star? Was it sculpted by tidal forces during a close encounter with a massive planet or stellar companion? The mystery deepens as they realize that conventional formation processes rarely produce objects with such extreme dimensions. Oumuamua challenges fundamental assumptions about how solid bodies evolve in alien solar systems, suggesting that other stellar neighborhoods operate under different rules or experience more violent events. The discovery represents a profound shift in perspective. For centuries, astronomy has involved studying distant objects through their light, stars, galaxies, and planets separated by vast chasms of space and time. Photons carry information across these distances, but they reveal only what can be inferred from electromagnetic radiation. Oumuamua brings the universe directly to our doorstep, offering the first opportunity to examine actual matter that formed around another star. It carries within its atoms and minerals the chemical signature of processes that occurred in a different part of the galaxy. Perhaps billions of years ago, when the Sun itself was younger and smaller, the irony settles slowly among astronomers. After decades of searching for signs of alien life through radio telescopes and space missions, the first confirmed visitor from beyond our solar system arrives unannounced and silent. It carries no messages, broadcasts no signals, and shows no signs of artificial construction. Instead, it offers something perhaps more profound, direct evidence that the galaxy recycles matter between star systems, sharing the products of planetary formation across vast distances and timescales. Yet even as telescopes gather data, Oumuamua continues its relentless journey outward from the Sun. By the time astronomers fully grasp the significance of their discovery, the visitor has already passed Earth's orbit and heads toward the outer solar system. Within months, it will fade beyond the reach of even the most powerful instruments, returning to the cold darkness between stars, where it will continue tumbling for millions more years until perhaps another stellar encounter briefly illuminates its ancient surface. The encounter lasts only weeks, but it marks the beginning of a new chapter in human understanding. Oumuamua proves that interstellar space teems with wandering objects, fragments of worlds that formed around other suns, now drifting through the galaxy like messages written in stone and ice. Each carries information about stellar evolution, planetary formation, and the chemical diversity of cosmic neighborhoods humanity may never visit directly. The universe, it seems, delivers samples of itself with patience that spans geological ages. As the visitor fades from view, scientists already wonder when the next messenger will arrive. Statistical calculations suggest Oumuamua represents not an anomaly, but the first glimpse of a vast population of interstellar travelers. The galaxy, it seems, shares its secrets more generously than anyone had imagined, one ancient fragment at a time, tumbling through the darkness toward whatever civilization happens to be watching the sky when they finally arrive. The telescopes that track Oumuamua reveal more than just its presence. They capture the ancient story written in the rhythm of its rotation and the subtle variations of reflected starlight. Every 7 hours and 20 minutes, the visitor completes one full tumble, presenting different faces to the sun as it spins through the void. This rotation carries the signature of whatever forces set it spinning, perhaps billions of years ago when it first broke free from its parent system, launched into the darkness by gravitational slingshots or catastrophic collisions that humanity can only imagine. Astronomers measure these brightness variations with exquisite precision, watching how the reflected sunlight waxes and wanes as different portions of the elongated surface catch and scatter the sun's rays. The data reveals something remarkable. Oumuamua's rotation appears remarkably stable, unchanged by any gravitational torques from the planets it passes or the differential heating it experiences as solar radiation warms one side while the other remains in shadow. This suggests the object has maintained its current spin for an extraordinarily long time, tumbling through interstellar space with the mechanical persistence of a cosmic gyroscope that remembers its original momentum across geological ages. The brightness curve itself tells a complex story. Rather than the simple sinusoidal variation expected from a uniformly reflective spinning cylinder, Oumuamua shows subtle asymmetries and secondary fluctuations that speak to surface irregularities preserved from its ancient past. Perhaps impact craters from primordial collisions create these variations. Or maybe the object retains the original texture imparted by whatever violent process sculpted its unusual form. Each peak and valley in the light curve represents a different facet catching sunlight, creating a photometric fingerprint as unique as a stellar birthmark. The surface itself tells a story of deep time and cosmic exposure that spans timescales almost beyond human comprehension. Spectroscopic analysis reveals not just the reddish coloration common to radiation-weathered objects, but subtle variations across different regions of the tumbling form that suggest a complex history of interstellar processing. Some areas appear slightly darker, others marginally more reflective, creating a patchwork pattern that speaks to millions of years of cosmic ray bombardment, solar-wind interactions during previous stellar encounters, and the gradual accumulation of interstellar dust upon its ancient flanks. Over these vast timescales, cosmic rays have gradually altered the surface chemistry one atom at a time, breaking molecular bonds and creating new compounds that exist nowhere on Earth. High-energy particles from distant supernovae and stellar winds have steadily gardened the uppermost layers of the object, mixing and redistributing material while implanting exotic isotopes formed in the nuclear furnaces of other stars. The result is a surface that bears the accumulated signature of galactic evolution, a palimpsest written by the radiation environment of interstellar space. The most intriguing aspect emerges from detailed photometry. The precise measurement of brightness changes over time, conducted by multiple observatories working in coordination. Oumuamua's light curve shows not just the expected variations from its elongated shape, but subtle secondary fluctuations that suggest surface features or compositional differences along its length. These variations remain consistent from one rotation to the next, indicating permanent features rather than temporary phenomena like outgassing jets or surface activity. Infrared observations conducted by space-based telescopes reveal another profound mystery. Oumuamua shows no signs of the water vapor, carbon monoxide, carbon dioxide, or other volatile gases that typically stream from comets when they approach the Sun. Despite receiving thousands of times more solar radiation than it experienced during its long journey through the near absolute zero of interstellar space, the visitor remains stubbornly inert. Either its surface has been so thoroughly processed by millions of years of cosmic radiation that no volatile materials remain accessible to sublimation, or it possesses a composition fundamentally different from the icy bodies that populate our own outer solar system. This absence of cometary activity puzzles scientists familiar with the behavior of objects from the Kuiper Belt and Oort cloud. These native solar system wanderers reliably begin sublimating their ices when solar heating reaches certain well-established thresholds, creating the characteristic tails and comas that make comets visible to amateur astronomers. Oumuamua receives far more intense heating as it swings past the Sun on its hyperbolic trajectory, yet remains as dry and unresponsive as ancient volcanic glass. The implication suggests either extreme depletion of volatile compounds through eons of interstellar weathering, or a fundamentally rocky composition unusual for objects that should have formed in the cold outer regions of another stellar system. Radio telescopes around the world join the observational campaign, their sensitive receivers listening across multiple frequency bands for any artificial signals that might emanate from the visitor. The Green Bank Observatory, Parkes Radio Telescope, and other facilities conduct systematic searches with the sensitivity to detect even weak transmissions that might indicate technological origin. The search reveals only the expected silence of empty space. Oumuamua broadcasts nothing, responds to nothing, and shows no deviation from the mechanical tumbling expected of an entirely inert object governed solely by the laws of celestial mechanics. Yet this very silence carries its own profound significance. It confirms that the first interstellar visitor discovered by humanity originates from natural processes rather than intelligent design, representing the galaxy's first confirmed delivery of raw material rather than manufactured artifacts. The absence of any technological signatures establishes Oumuamua as a natural phenomenon, a fragment of planetary formation processes that occurred around another star, now offering direct samples of alien world-building for scientific analysis. The rotation data also reveals something profound about the gravitational environment Oumuamua has experienced during its interstellar journey. The stable 7-hour and 20-minute period suggests the object has avoided significant collisions or close gravitational encounters for millions of years. Any approach within the gravitational influence of massive bodies would likely alter its spin through tidal forces. Yet, Oumuamua maintains the mechanical memory of whatever event first set it tumbling. This rotational persistence implies a remarkably empty journey through interstellar space, threading between star systems without experiencing the gravitational perturbations that might fundamentally change its characteristics. Detailed analysis of the brightness variations allows astronomers to construct crude but revealing maps of surface reflectivity variations. These photometric maps suggest that Oumuamua's elongated form may not be perfectly smooth, but instead shows systematic variations that could represent impact features from ancient collisions, compositional differences inherited from its formation, or the preserved texture of whatever catastrophic fragmentation event originally liberated it from its parent body. The object carries upon its surface the accumulated history of its interstellar journey, a record written in microscopic impacts, radiation damage, and chemical alteration that spans timescales comparable to the age of complex life on Earth. The thermal observations provide yet another layer of mystery that deepens with each night of observation. Theoretical models predict that an object with Oumuamua's size, shape, and rotation period should show characteristic temperature patterns as different regions experience heating and cooling during each tumble through space. Yet the measured infrared emission suggests more complex thermal behavior than simple models predict, possibly indicating variations in surface texture, composition, thermal conductivity, or subsurface structure along the object's considerable length. These subtle thermal differences hint at a formation history more complicated than simple fragmentation from a larger homogeneous body. Perhaps most remarkably, the sunlight reflected from Oumuamua carries within its spectrum the chemical fingerprints of elements that condensed from the stellar winds and supernova ejecta of another star system. Iron, silicon, magnesium, aluminum, and other heavy elements show absorption features subtly but measurably different from their solar system counterparts, variations that speak to the nuclear processes occurring in the core of a different sun billions of years ago when that star was synthesizing elements and distributing them through stellar winds into the surrounding interstellar medium. This visitor literally brings samples of stellar nucleosynthesis from across the galaxy, allowing Earth-based spectrographs to analyze matter that formed under different conditions in a different stellar environment. The isotopic ratios preserved in its composition reflect the neutron flux, temperature, and pressure conditions that existed in another star's core during the epochs of heavy element formation. offering a direct window into stellar evolution processes occurring in distant parts of the galaxy. The accumulated observations paint a picture of an object shaped by processes that operate on timescales almost incomprehensible to human experience, yet recorded with mechanical precision in its rotation and surface properties. Oumuamua has tumbled through the galaxy for perhaps hundreds of millions of years, its surface slowly darkening and texturing under the constant bombardment of cosmic radiation, while its deep interior remains essentially unchanged from the moment of its formation in another stellar system, when the galaxy itself was younger and contained different populations of stars. As Oumuamua swings around the Sun and begins its outbound journey toward the outer solar system, something unexpected happens that will puzzle astronomers for years to come. The object accelerates, not dramatically, but measurably, beyond what gravitational forces alone should produce. This small but persistent deviation from predicted orbital mechanics represents one of the most intriguing mysteries in modern astronomy, challenging fundamental assumptions about how inert objects behave in the well-understood gravitational environment of the inner solar system. The acceleration becomes apparent through precise astrometric measurements conducted by multiple observatories tracking the visitor's position against the background stars, expected to follow a perfect hyperbolic trajectory determined solely by the Sun's gravitational field. Oumuamua instead shows systematic deviations that grow larger with each passing day. The effect is subtle, approximately 0.25 millimeters per second squared, but far exceeds the precision limits of modern tracking systems. Something beyond gravity is pushing the object away from the Sun with gentle but persistent force. Initially, astronomers suspect measurement error or systematic biases in their observations. The tracking of small, distant objects requires extraordinary precision, accounting for atmospheric refraction, telescope flexure, detector calibration, and dozens of other potential sources of systematic uncertainty. Teams at different observatories cross-check their measurements, refine their calibration procedures, and conduct independent analyses of the same data. Yet the anomalous acceleration persists across all instruments and analysis techniques, growing stronger as the object approaches perihelion and gradually diminishing as it recedes toward interstellar space. The most obvious explanation invokes cometary outgassing, the sublimation of volatile ices that creates rocket-like thrust as gas molecules escape preferentially from the sunward-facing hemisphere. Countless comets have displayed similar non-gravitational accelerations as solar heating drives water vapor, carbon monoxide, and other gases from their surfaces. Yet, Oumuamua shows no spectroscopic evidence of gas emission, no detectable coma or tail, and no thermal signature consistent with active sublimation. Every attempt to detect outgassing with increasingly sensitive instruments reveals only the silence of an apparently inert object. This absence of observable gas emission while simultaneously experiencing non-gravitational acceleration creates a profound puzzle. The amount of thrust required to explain Oumuamua's orbital deviation would typically require substantial mass loss through sublimation, enough to create easily detectable spectral signatures in any comprehensive survey. Yet the most sensitive observations reveal no trace of escaping gases, no dust production, and no thermal anomalies consistent with active volatile loss. The object appears to accelerate through some mechanism that operates without leaving the usual forensic evidence of cometary activity. Scientists propose increasingly exotic explanations as conventional models fail to reconcile the observations. Perhaps Oumuamua possesses an unusual composition that outgasses materials undetectable by standard spectroscopic techniques, maybe nitrogen ice, solid hydrogen, or other exotic volatiles sublime without producing observable signatures in the wavelength ranges typically monitored by astronomical instruments. Some researchers suggest that subsurface cavities might trap and release gases in ways that minimize observable emission while still producing measurable thrust. The solar radiation pressure hypothesis gains attention as teams calculate whether photons alone might push the object off its gravitational trajectory. Sunlight carries momentum, and when photons reflect from or are absorbed by solid surfaces, they impart tiny but cumulative forces. For objects with extremely low density or unusually high surface area to mass ratios, radiation pressure can become significant. Yet calculations reveal that Oumuamua would need to be far less dense than any known natural material, essentially a hollow shell or fluffy aggregate, to experience the observed acceleration through radiation pressure alone. The debate intensifies as researchers explore whether the object's unusual elongated shape might enhance radiation pressure effects through mechanisms not accounted for in standard models. Perhaps the tumbling motion creates asymmetric heating patterns that generate preferential photon emission from certain regions, creating a subtle but persistent photon rocket effect. Or maybe the surface properties vary along the object's length in ways that create differential radiation pressure, imparting net thrust through purely optical processes rather than material outgassing. More speculative theories emerge as conventional explanations prove inadequate. Some researchers wonder whether Oumuamua might represent a fragment of artificial material, perhaps part of a solar sail or other technological artifact from an alien civilization. The object's extreme dimensions and anomalous acceleration bear some resemblance to proposed interstellar probe designs, though no other characteristics support artificial origin. The hypothesis generates considerable public interest, but finds little support among astronomers familiar with the object's otherwise natural properties and behavior. Alternative scenarios invoke more exotic physics, including modifications to gravitational theory on small scales, interactions with dark matter, or previously unknown forces that operate in the interstellar medium but remain undetected in laboratory experiments. These explanations stretch the boundaries of established physics, requiring new fundamental forces or modifications to general relativity that would have profound implications far beyond the behavior of a single interstellar visitor. Most researchers regard such radical departures from known physics as unnecessary, given the wealth of more conventional possibilities still under investigation. The thermal evolution of Oumuamua as it approaches and recedes from the Sun provides additional clues to the acceleration mechanism. Detailed infrared observations reveal complex heating and cooling patterns that suggest variations in thermal properties along the object's surface. Perhaps some regions retain volatile materials, while others have been stripped clean by interstellar weathering, creating localized outgassing that escapes detection due to its highly collimated or temporally variable nature. The tumbling motion might concentrate gas emission into narrow jets that point away from Earth during crucial observation windows. Numerical simulations attempt to reproduce the observed acceleration using increasingly sophisticated models of surface physics, thermal evolution, and volatile transport. These calculations explore how trace amounts of various gases might behave under the extreme thermal cycling experienced during solar approach, investigating whether exotic sublimation scenarios could produce thrust without detectable emission signatures. Some models invoke subsurface layering, where radiation-processed surface crusts trap volatile-rich materials that sublimate explosively during thermal stress, creating brief episodes of the thrust that average out to the observed acceleration over longer time scales. The mystery deepens as follow-up observations with the most powerful telescopes fail to resolve the discrepancy between orbital mechanics and observable properties. Oumuamua continues to accelerate away from the Sun while showing no signs of the material loss that should accompany such behavior. The object maintains its dark, apparently inert surface, even as something invisible pushes it along its trajectory with the patience of a gentle but persistent wind. Perhaps the most profound implication emerges from the recognition that Oumuamua challenges fundamental assumptions about the relationship between observable properties and dynamical behavior. For centuries, astronomers have relied on the principle that objects displaying similar spectroscopic and thermal characteristics should behave similarly under identical gravitational and radiative environments. Oumuamua suggests that interstellar objects might possess properties or undergo processes not represented in solar system analogues, carrying within their compositions or structures the signature of formation conditions or evolutionary pathways unknown in our local cosmic neighborhood. The acceleration mystery transforms Oumuamua from a simple visitor into a harbinger of discoveries yet to come. If the first confirmed interstellar object displays behavior that defies easy explanation, what surprises await in the study of future visitors? The puzzle suggests that interstellar space shapes objects in ways that escape prediction based solely on solar system experience, hinting at physical processes, compositional variations, or evolutionary pathways that operate across the galaxy but remain invisible until samples arrive at our doorstep. As Oumuamua fades beyond the reach of even the most powerful telescopes, it carries its secrets back into the darkness between stars. The acceleration that puzzled astronomers continues to act upon the visitor, gently nudging it along trajectories that will carry it far from the sun toward whatever stellar encounters await in the distant future. The mystery remains unsolved, a reminder that the universe still harbors phenomena that challenge human understanding even when they pass close enough to touch. Between the stars, where temperatures hover just a few degrees above absolute zero and matter exists in conditions impossible to replicate on Earth, strange transformations occur over timescales that dwarf human civilization. The space that separates stellar systems is not truly empty, but filled with a tenuous medium of gas, dust, and radiation that slowly works upon any solid object wandering through its domain. Oumuamua spent millions of years immersed in this environment, its surface and structure gradually modified by processes that operate with the patience of geological time. The interstellar medium contains roughly 1 atom per cubic centimeter, a vacuum more perfect than anything achievable in terrestrial laboratories, yet dense enough to exert cumulative effects over cosmic distances. These atoms, primarily hydrogen, with traces of heavier elements forged in stellar cores, drift through space at velocities that reflect the violent events of their origin. Supernova shockwaves accelerate some particles to near relativistic speeds, creating cosmic rays that penetrate deep into any solid matter they encounter. Other atoms move more sedately, carried by stellar winds or the gentle pressure of radiation from distant stars. For an object like Oumuamua traveling at interstellar velocities, collisions with this sparse material occur with the frequency and intensity of a cosmic sandblasting process. Each impact, though involving only individual atoms or small molecules, transfers momentum and energy to the surface over millions of years. This bombardment gradually erodes the uppermost layers of solid material, stripping away original surface features and creating new compounds through nuclear reactions and chemical processing. The cumulative effect transforms surfaces in ways that have no analog in the protected environment of our inner solar system. Cosmic rays, high-energy particles accelerated by magnetic fields around neutron stars, black holes, and supernova remnants, penetrate even deeper into solid matter. These relativistic projectiles possess enough energy to shatter atomic nuclei, creating cascades of secondary particles that propagate through crystalline structures like microscopic explosions. The radiation damage accumulates over time, breaking molecular bonds, creating lattice defects, and gradually altering the physical properties of materials formed under the relatively benign conditions that prevail during planetary formation. The constant flux of cosmic radiation also drives nuclear reactions within the surface layers of interstellar objects. Galactic cosmic rays contain protons, alpha particles, and heavier nuclei that can induce spallation reactions when they strike atomic targets. These collisions fragment heavy elements into lighter isotopes, create exotic radioactive species with no terrestrial analogues, and gradually change the elemental composition of exposed surfaces. A silicon atom struck by a high-energy proton might break apart into aluminum and other fragments, while bombardment by cosmic ray nuclei can transmute common elements into rare isotopes that serve as traces of interstellar exposure. The temperature environment of interstellar space creates its own unique chemical laboratory. At just a few Kelvin above absolute zero, thermal motion nearly ceases, allowing quantum mechanical effects to dominate molecular behavior. Phase transitions that never occur under terrestrial conditions become possible, while familiar materials adopt crystalline structures unknown at higher temperatures. Ice formed in interstellar conditions possesses different density, hardness, and optical properties than water ice found on Earth or in the outer solar system, creating surfaces that reflect and absorb light in characteristic ways. This extreme cold also preserves information about cosmic history within the crystalline structure of solid materials. Defects created by radiation damage remain frozen in place for millions of years, accumulating like archaeological layers that record the intensity and composition of cosmic ray fluxes encountered during interstellar travel. The distribution of these defects provides a detailed history of the radiation environment experienced by wandering objects, revealing information about the stellar populations, supernova rates, and magnetic field configurations they encountered during their journeys between star systems. Magnetic fields permeating interstellar space interact with any metallic components within solid objects, inducing electrical currents that dissipate energy as heat. Though the fields are weak by terrestrial standards, typically a few microgauss, their effects accumulate over vast time scales. Iron-bearing minerals experience gradual magnetic reordering, while conducting materials develop surface charge distributions that influence how they interact with the charged particle environment. These electromagnetic effects contribute to the complex weathering processes that modify interstellar travelers over geological time. The sparse dust grains drifting through interstellar space also contribute to surface modification through direct impact. These microscopic particles, typically composed of silicates, carbon compounds, or ice, strike wandering objects at relative velocities measured in tens of kilometers per second. Each collision vaporizes a tiny amount of surface material while depositing foreign atoms and molecules that gradually alter surface composition. The cumulative effect of countless such impacts creates a distinctive patina that carries the chemical signature of interstellar matter accumulated during the journey between star systems. Solar wind from distant stars adds another layer of complexity to interstellar weathering. Though much weaker than the solar wind experienced in our inner solar system, the combined effect of stellar winds from multiple sources creates a diffuse plasma environment that slowly sputters atoms from exposed surfaces. This process operates most efficiently on materials with low binding energies, gradually removing volatile components while concentrating refractory elements that resist plasma erosion. The result is surface compositions that evolve toward increasingly inert, radiation-resistant configurations. Perhaps most remarkably, the low-temperature chemistry of interstellar space enables reactions that cannot occur under terrestrial conditions. Free radicals created by radiation damage remain stable for millions of years in the near absolute zero environment, allowing complex organic synthesis to proceed through pathways impossible at higher temperatures. Simple molecules like carbon monoxide, water, and methane can combine to form increasingly complex organic compounds through radical reactions catalyzed by cosmic ray bombardment. These processes might explain the dark, carbon-rich surfaces observed on many objects that have experienced extended interstellar exposure. The accumulated effects of millions of years in interstellar space create objects with properties unlike anything found in our solar system. Surfaces darkened by radiation damage and organic synthesis reflect only a few % of incident light, giving wanderers like Oumuamua their characteristic low albedo. Crystalline structures altered by cosmic ray bombardment adopt new configurations that change mechanical properties, thermal conductivity, and optical characteristics. Chemical compositions shift toward radiation-resistant configurations through selective removal of volatile elements and preferential retention of refractory components. These transformation processes operate so slowly that they remain invisible on human timescales. Yet, their cumulative effects over cosmic time create fundamental changes in material properties. An object that began its journey as a typical rocky or icy fragment of planetary formation emerges from interstellar space as something qualitatively different, a hybrid material that carries within its structure the integrated signature of galactic evolution. The composition and properties of such objects reflect not only their original formation conditions, but also the radiation environment, chemical composition, and physical conditions they encountered during their wandering through the galaxy. Understanding these interstellar weathering processes becomes crucial for interpreting observations of objects like Oumuamua. The surface properties, chemical composition, and physical characteristics visible to telescopes represent the end product of complex evolutionary pathways that operate over timescales comparable to the age of complex life on Earth. Decoding the information preserved in these weathered surfaces requires understanding both the original formation processes that created the objects and the subsequent modification processes that transformed them during their journey through interstellar space. The recognition that interstellar weathering fundamentally alters the properties of wandering objects has profound implications for astronomy. It suggests that direct samples of alien planetary formation, the original goal of studying interstellar visitors, might be heavily overprinted by subsequent processing in the galactic environment. Yet this limitation carries its own scientific value, as the weathering signatures themselves provide information about conditions in interstellar space that cannot be obtained through any other means. Each visitor becomes a probe that has sampled the radiation environment, chemical composition, and physical conditions along its trajectory through the galaxy, carrying within its modified structure a record of cosmic evolution written in the universal language of atomic physics. The discovery of Oumuamua forces astronomers to confront an uncomfortable statistical reality that has lurked at the edges of theoretical models for decades. If such objects pass through the inner solar system frequently enough for humanity to detect one during the brief historical moment when telescopes possess sufficient sensitivity, then the galaxy must contain a population of wandering interstellar fragments numbering in the quintillions, a vast census of planetary debris drifting between the stars in quantities that challenge basic assumptions about stellar system formation and evolution. Calculations begin with deceptively simple questions that lead to profound implications. Oumuamua measures roughly 400 meters in length, making it large enough to detect with modern ground-based telescopes, but small enough that countless similar objects might have passed unnoticed in previous decades. The object crosses the ecliptic plane at a steep angle, following a trajectory that brings it close enough to the Sun for solar heating to enhance its visibility against the background of space. Yet the detection occurred almost by accident, during routine asteroid surveys designed to catalog potentially hazardous objects that might threaten Earth. The geometry of detection reveals the first statistical challenge. Oumuamua approaches from the direction of the constellation Lyra, following one of countless possible trajectories that could bring an interstellar visitor into the inner solar system. Only objects passing within a few astronomical units of the Sun become bright enough for detection with current telescopes, creating a narrow detection zone that represents a tiny fraction of the vast volume through which such objects might pass. For every visitor that enters this detection zone, thousands of others must pass through the outer solar system unobserved, their presence revealed only by gravitational perturbations too subtle for current instruments to measure. Theoretical models attempt to estimate the total population of interstellar objects based on the single confirmed detection. The calculations require assumptions about size distributions, velocity dispersions, spatial densities, and detection probabilities that remain poorly constrained by observational data. Yet even conservative estimates suggest that objects similar to Oumuamua pass through the solar system at rates measured in several per year, with smaller fragments arriving far more frequently and larger objects representing increasingly rare events that might occur only once per decade or century. The implied population density in interstellar space reaches staggering proportions. If the solar neighborhood contains enough wandering objects to supply the observed detection rate, then every cubic parsec of galactic space must harbor thousands of fragments ranging from boulder-sized chunks to asteroid-scale bodies. This population would represent a previously invisible component of galactic matter, hiding in the darkness between stars while contributing significantly to the total mass budget of the galaxy. The discovery of a single object hints at a vast, hidden population that has remained undetected throughout the entire history of astronomy. These statistical implications force a fundamental reconsideration of planetary formation processes and their efficiency in retaining solid material within stellar systems. Traditional models suggest that planetary accretion proceeds through relatively gentle processes that preserve most solid material within the gravitational domain of the parent star. Yet the inferred population of interstellar wanderers implies that planetary formation operates as a profoundly wasteful process, ejecting substantial fractions of solid material into interstellar space through gravitational interactions. Close encounters and catastrophic events that scatter debris across galactic distances. The timescales involved in populating interstellar space with such vast numbers of objects require ejection processes operating throughout galactic history. Young stellar systems, still surrounded by protoplanetary disks and debris from recent formation, might contribute fresh material through gravitational scattering by massive planets or stellar companions. Mature systems could lose material through later catastrophic events, asteroid belt disruption, planetary collisions, or close encounters with passing stars that destabilize previously stable orbits. Even ancient stellar systems might continue contributing material through processes operating on timescales comparable to the age of the galaxy itself. The velocity distribution of interstellar objects provides additional constraints on their origins and the processes responsible for their ejection. Oumuamua enters the solar system at approximately 26 kilometers per second relative to the Sun, a velocity consistent with objects originating from stellar systems in the solar neighborhood and acquiring modest additional velocity through gravitational interactions during ejection. Objects ejected by more violent processes, supernova explosions, close stellar encounters, or disruption by compact objects would display much higher velocities that should be detectable through their distinctive orbital characteristics. The observed velocity suggests that most interstellar objects originate from relatively gentle ejection processes operating in normal stellar systems rather than exotic catastrophic events. This implies that the production of interstellar wanderers represents a natural consequence of planetary system evolution rather than a rare outcome of unusual circumstances. Every stellar system probably contributes to the interstellar population through ongoing processes that operate throughout the system's lifetime, gradually leaking solid material into the galactic environment through mechanisms that remain poorly understood. The chemical and physical diversity expected within such a vast population boggles the imagination. Objects originating from different stellar systems would carry the compositional signatures of their formation environments, the heavy element abundances, isotopic ratios, and mineralogical characteristics that reflect the nuclear processing history of their parent stars. Some wanderers might preserve primitive compositions from the earliest epochs of planetary formation, while others could represent the processed products of advanced planetary evolution. carrying within their structure the signatures of differentiation, volcanism, and surface modification processes that operated under alien conditions. The range of formation environments represented by interstellar objects encompasses the full diversity of stellar populations and galactic chemical evolution. Objects ejected from metal-poor stars in the galactic halo would possess compositions dominated by hydrogen and helium, with only trace amounts of heavier elements, while fragments from metal-rich systems in the galactic disk might contain complex minerals and organic compounds unknown in our solar system. Each wanderer represents a sample of conditions that existed during planetary formation in different parts of the galaxy at different epochs in cosmic history. The age distribution of the interstellar population adds another dimension to the statistical puzzle. Objects ejected billions of years ago from the first generation of planetary systems might still wander through galactic space, their surfaces modified by eons of cosmic weathering, but their interiors preserving information about conditions during the galaxy's youth. More recent ejecta from contemporary stellar systems would display less weathering and might retain surface compositions closer to their original formation states. The mixture of ancient and modern wanderers creates a temporal sampling of galactic evolution encoded in the physical properties of objects drifting through interstellar space. The three-dimensional distribution of interstellar objects throughout the galaxy reflects the complex dynamics of stellar motion and galactic rotation. Objects ejected from stars in different parts of the galaxy follow orbital paths determined by the gravitational potential of the entire galactic disk, creating streaming patterns and density variations that evolve over hundreds of millions of years. The solar system's motion through this population creates a time-variable flux of visitors with characteristics that depend on the local stellar neighborhood and its formation history. Perhaps most remarkably, the statistical analysis suggests that interstellar objects might represent the galaxy's primary mechanism for sharing solid material between stellar systems, while electromagnetic radiation and cosmic rays provide information transfer across galactic distances. Wandering objects offer the only means by which actual samples of planetary formation can travel between star systems. This process operates slowly compared to human timescales, requiring millions of years for objects to traverse the distances between stellar neighbors. Yet it provides a mechanism for chemical and perhaps even biological exchange that connects all planetary systems within a common galactic ecosystem. The detection of Oumuamua thus represents not just the discovery of an individual object, but the first glimpse of a vast, previously invisible component of galactic ecology. The statistics of this single detection imply the existence of countless wanderers carrying samples of alien world-building processes through the darkness between stars, each preserving within its composition and structure information about planetary formation conditions that prevailed in different parts of the galaxy at different times in cosmic history. The galaxy, it seems, has been conducting a natural experiment in comparative planetary science for billions of years, scattering the results through interstellar space, where patient observers might eventually decode the messages written in stone and ice. The loneliness of first contact dissolves under statistical analysis, replaced by the recognition that humanity exists within a galaxy teeming with wandering fragments of alien worlds. Each carries its own story of formation, evolution, and ejection, contributing to a vast archive of planetary science distributed throughout galactic space. The challenge facing astronomy is no longer detecting these visitors, but developing the theoretical framework and observational capabilities necessary to decode the information they carry about the diversity and evolution of planetary systems throughout the galaxy. 2 years after Oumuamua fades beyond the reach of telescopes, another visitor arrives to offer humanity a second glimpse into the wandering population of interstellar space. On August 30th, 2019, amateur astronomer Gennady Borisov discovers a fuzzy object moving through the constellation Gemini using a modest telescope he constructed himself at the Margot Observatory in Crimea, initial observations suggest nothing unusual, perhaps another comet from the outer reaches of our solar system beginning its long fall toward the Sun. Yet, within days, orbital calculations reveal something extraordinary. This visitor also follows a hyperbolic trajectory that originates from beyond the gravitational domain of our star. The object receives the designation 2I/Borisov, marking humanity's second confirmed interstellar visitor and the first to display the familiar characteristics of cometary activity. Unlike the enigmatic Oumuamua, which remained stubbornly inert throughout its passage, Borisov immediately begins developing the classic signatures of sublimating ice as solar radiation heats its surface. A faint coma of gas and dust surrounds the nucleus, growing brighter and more extensive as the comet approaches perihelion in its journey through the inner solar system. Spectroscopic observations reveal water vapor streaming from Borisov's nucleus at rates comparable to comets native to our solar system. The familiar molecular signatures of H2O, Cn, and C2 appear in the comet's spectrum, indicating that basic chemistry operates similarly in the alien stellar system where this visitor formed. Yet subtle differences emerge in the relative abundances of various species, suggesting compositional variations that reflect different formation conditions or evolutionary pathways compared to solar system analogues. The nucleus itself presents a more conventional appearance than Oumuamua's extreme elongated form. Estimates based on brightness variations and thermal modeling suggest Borisov measures roughly 1 kilometer in diameter, making it comparable in size to typical short-period comets but significantly larger than most objects ejected from the Kuiper belt. The surface displays the characteristic low reflectivity of comet nuclei, darkened by organic compounds and radiation processing during its journey through interstellar space. Detailed photometric monitoring reveals rotation periods and light curve variations consistent with an irregularly shaped nucleus tumbling through space. The amplitude of brightness changes suggests moderate elongation, perhaps twice as long as wide, but nothing approaching the extreme proportions that made Oumuamua so unusual among known solar system objects. Borisov appears to represent a more typical fragment of planetary formation, similar in basic characteristics to comets found in our own outer solar system, but carrying the chemical fingerprints of formation around another star. The comet's trajectory provides clues about its origin and the velocity it acquired during ejection from its parent system. Borisov approaches the Sun at approximately 32 kilometers per second relative to our star, somewhat faster than Oumuamua but still consistent with origins in the local stellar neighborhood rather than exotic high-velocity processes. The orbital inclination and approach direction suggest the comet originated from a different region of nearby space, indicating that interstellar visitors arrive from various directions as the solar system moves through the local population of wandering objects. As Borisov develops its coma and tail, astronomers gain the first opportunity to study the detailed composition of volatiles from another stellar system. Mass spectrometry of the sublimating gases reveals isotopic ratios that provide direct information about nuclear processing in the comet's parent star. The deuterium to hydrogen ratio in water vapor shows subtle but measurable differences from solar system norms, indicating formation in a stellar environment with slightly different nuclear burning conditions or chemical evolution history. Carbon monoxide emission from Borisov's nucleus displays abundances significantly higher than typical solar system comets, suggesting formation in a colder region of its parent system or different chemical processes during the accretion of its constituent materials. This compositional difference implies that the chemistry of planetary formation varies between stellar systems, perhaps reflecting different temperatures, densities, or chemical compositions in the outer regions where comets typically form. The dust particles ejected from Borisov's nucleus carry additional information about solid materials that condensed in an alien stellar environment. Polarimetry measurements reveal grain properties similar to solar system comet dust, but with subtle variations in size distribution and optical characteristics that hint at different formation or processing conditions. Some particles display unusual spectral signatures that suggest mineral phases or crystalline structures not commonly observed in native solar system materials. The temporal evolution of Borisov's activity provides insights into the subsurface structure and thermal properties of interstellar comet nuclei. As solar heating penetrates into the nucleus, sublimation patterns reveal information about porosity, thermal conductivity, and the distribution of volatile materials throughout the interior. These characteristics reflect both the original accretion processes that assembled the comet and subsequent modification during its long journey through interstellar space. Perhaps most significantly, Borisov demonstrates that interstellar visitors can preserve familiar chemical signatures despite millions of years of cosmic weathering. The detection of common molecules like water, carbon monoxide, and various organic compounds suggests that basic chemical processes operate similarly throughout the galaxy, creating materials recognizable to observers familiar with solar system chemistry. This chemical continuity implies that the building blocks of planetary systems remain consistent across different stellar environments. The comet's behavior as it approaches and recedes from the Sun follows patterns established by decades of studying solar system comets, yet with distinctive characteristics that reflect its alien origin. Gas production rates increase and decrease with solar distance according to familiar thermal models, but with scaling factors that suggest different ice compositions or sublimation kinetics compared to native comets. These subtle differences provide windows into the physical conditions that prevailed during formation in another stellar system. Observations of Borisov's dust tail reveal complex dynamics as solar radiation pressure and solar wind interactions shape the distribution of ejected particles. The tail's morphology and evolution provide information about particle sizes, densities, and emission velocities that reflect the physical processes operating within the nucleus. Comparison with solar system comet tails reveals both similarities and differences that illuminate the range of properties exhibited by comets formed in different stellar environments. The discovery of Borisov confirms theoretical predictions about the population of interstellar objects and their diversity of physical characteristics. While Oumuamua represented an extreme example with unusual properties that challenged conventional understanding, Borisov displays characteristics more consistent with expectations based on solar system experience. This diversity suggests that interstellar space contains representatives of the full range of objects produced by planetary formation processes, from conventional icy bodies to exotic fragments with properties unlike anything found in our local cosmic neighborhood. The chemical analysis of Borisov's composition provides the first direct measurement of volatile materials from another stellar system, offering unprecedented insights into the chemical conditions that prevailed during planetary formation around a different star. These measurements represent a form of stellar archaeology, using the preserved composition of ancient ice to reconstruct the chemical environment that existed in an alien stellar system billions of years ago when planets were forming from the primordial disk of gas and dust. As Borisov continues its journey back toward interstellar space, it carries with it the satisfaction of confirming that humanity possesses the observational capabilities necessary to study interstellar visitors in detail. The comet's conventional behavior and familiar chemistry provide reassurance that alien planetary formation processes operate according to physical principles similar to those governing our own solar system, while its distinctive characteristics offer glimpses of the variations and diversity that exist among stellar systems throughout the galaxy. The discoveries of Oumuamua and Borisov awaken the astronomical community to a new reality. Interstellar visitors pass through our solar system regularly, but only systematic surveys with sufficient sensitivity can detect them during their brief passages through the inner regions where solar heating makes them visible. This recognition triggers a transformation in observational astronomy, shifting from serendipitous discoveries to coordinated campaigns designed to identify and study these cosmic messengers before they fade back into the darkness between stars. Ground-based surveys expand their search parameters to include objects with orbital characteristics consistent with interstellar origin. The Catalina Sky Survey, Linear, and other asteroid detection programs modify their software to flag objects displaying the high velocities and unusual orbital inclinations that mark visitors from beyond the solar system. These automated systems process thousands of observations each night, comparing new detections against databases of known objects and highlighting anything that displays motion inconsistent with gravitational binding to the Sun. The Large Synoptic Survey Telescope, now known as the Vera Rubin Observatory, promises to revolutionize the detection of interstellar objects through its unprecedented combination of wide field coverage, deep sensitivity, and rapid cadence observations. The facility's planned survey will repeatedly image the entire visible sky every few nights, creating a comprehensive census of moving objects that should detect interstellar visitors within days of their entry into the observable region of the solar system. European and Asian observatories contribute to the emerging network through coordinated observations and data sharing agreements that ensure rapid follow-up of candidate interstellar objects. The European Space Agency's Gaia mission provides precise astrometric measurements that help refine orbital determinations, while ground-based spectrographs around the world stand ready to analyze the composition and physical properties of confirmed visitors. This international cooperation represents a new model for astronomical research, uniting observatories across continents in pursuit of objects that remain visible for only brief windows of time. Space-based telescopes offer unique advantages for studying interstellar visitors, providing continuous observations uninterrupted by weather, atmospheric turbulence, or the day-night cycle that limits ground-based surveys. The Hubble Space Telescope demonstrates these capabilities through detailed observations of both Oumuamua and Borisov, capturing high-resolution images and precise photometry impossible to achieve from Earth's surface. Future space missions specifically designed for solar system surveillance could detect interstellar objects earlier in their approach, providing longer observation windows for detailed study. The detection problem involves more than simply identifying fast-moving objects against the stellar background. Interstellar visitors display characteristic motion that distinguishes them from native solar system objects, but recognizing these signatures requires sophisticated orbital analysis and statistical modeling. Objects approaching from interstellar space initially appear to follow normal elliptical orbits, only revealing their true hyperbolic nature after sufficient observations accumulate to determine their trajectories precisely. Automated detection algorithms must balance sensitivity against false positive rates, distinguishing genuine interstellar visitors from measurement errors, instrumental artifacts, and exotic solar system objects with unusual orbital characteristics. Machine learning techniques help identify patterns in orbital data that indicate interstellar origin, training neural networks on the subtle signatures that distinguish bound from unbound trajectories. These computational approaches become essential as survey telescopes generate observation rates that exceed human capacity for manual analysis. The coordination of follow-up observations presents logistical challenges that require international cooperation and rapid communication networks. Once a candidate interstellar object is identified, astronomers have only days or weeks to gather detailed observations before the visitor fades beyond detection limits. This time, pressure demands pre-arranged observing protocols, automated alert systems, and flexible scheduling that can redirect major telescopes toward targets of opportunity with minimal delay. Spectroscopic observations present particular challenges due to the faintness of most interstellar visitors and their rapid motion across the sky. Obtaining sufficient signal-to-noise ratios for compositional analysis requires the largest telescopes equipped with the most sensitive spectrographs, often pushing instruments to their detection limits. The development of new detector technologies and observational techniques specifically optimized for faint, fast-moving targets becomes a priority for maximizing the scientific return from these rare encounters. The photometric monitoring necessary to determine rotation periods, surface properties, and activity levels requires sustained observations over multiple nights using telescopes distributed around the globe. International collaborations enable around-the-clock coverage as objects move through different longitude zones, maintaining continuous observations despite the Earth's rotation. These campaigns generate enormous datasets that require sophisticated analysis techniques to extract physical parameters from complex light curves. Theoretical modeling plays an increasingly important role in interpreting observations and predicting the properties of future visitors. Computer simulations of planetary formation and evolution help astronomers understand the processes that create and eject interstellar objects, while models of interstellar weathering predict how cosmic environments modify surfaces and compositions during long journeys between star systems. These theoretical frameworks guide observational strategies and help interpret the significance of measured properties. The recognition that interstellar objects represent samples of alien planetary systems transforms their study from curiosity-driven research to a new branch of comparative planetology. Each visitor carries information about formation conditions, chemical evolution, and physical processes that operated in different stellar environments, providing unique insights into the diversity of planetary systems throughout the galaxy. This perspective elevates interstellar object research to a high priority within the broader goals of astrobiology and exoplanet science. Archive searches through historical astronomical data reveal tantalizing hints that previous interstellar visitors may have passed unrecognized through the solar system before modern detection capabilities existed. Unusual objects observed in past decades display orbital characteristics or physical properties consistent with interstellar origin, though their true nature remains uncertain due to limited observational data. These retrospective analyses suggest that the rate of interstellar visitor detection may increase dramatically as survey capabilities improve. The development of specialized instrumentation for rapid response observations becomes a priority for major observatories. Instruments optimized for spectroscopy of faint, fast-moving targets require different design criteria than those intended for stationary celestial objects. New detector technologies, adaptive optics systems, and telescope control software enable observations that would have been impossible during the era when Oumuamua was discovered. Public engagement with interstellar object discoveries demonstrates the broad appeal of these cosmic visitors beyond the professional astronomical community. The recognition that humanity can directly study samples of alien worlds captures imaginations and generates support for continued investment in survey telescopes and follow-up observations. Educational programs help citizen scientists contribute to detection efforts while fostering public understanding of the scientific significance of these discoveries. As observational capabilities expand and detection rates increase, the study of interstellar objects evolves from individual case studies to statistical analyses of population properties. Surveys of dozens or hundreds of visitors will reveal correlations between physical properties, compositional characteristics, and orbital parameters that illuminate the processes responsible for their creation and ejection. This transition from anecdotal observations to systematic science marks the maturation of a new field within astronomy. The sky survey programs that will dominate the next decade promise to transform interstellar object research from a serendipitous endeavor to a systematic census of alien planetary materials. With patience and persistence, These automated sentinels will detect dozens of visitors each year, building a comprehensive database of physical properties and compositional characteristics that reveals the diversity of planetary formation throughout the galaxy. Each new detection adds another piece to the growing puzzle of cosmic evolution written in the language of stone and ice. When the third confirmed interstellar visitor appears in observational data from the Atlas survey in early 2023, astronomers approach its analysis with expectations shaped by the dramatic differences between Oumuamua and Borisov. The new object, designated 3I/Atlas, emerges from routine sky patrol observations as another fast-moving speck following a hyperbolic trajectory that confirms its extrasolar origin. Yet, unlike its predecessors, this visitor displays behavior that appears almost mundane in its adherence to simple gravitational mechanics, offering researchers their first opportunity to study an interstellar object that behaves exactly as theoretical models predict. Initial tracking of 3I/Atlas reveals an orbit that follows pure Keplerian mechanics with no detectable deviations from gravitational predictions. Unlike Oumuamua's mysterious acceleration or Borisov's complex outgassing patterns, this visitor traces a perfect hyperbolic path, determined solely by the Sun's gravitational field and its initial velocity vector. The absence of non-gravitational forces simplifies orbital analysis, while highlighting how unusual the previous visitors actually were in displaying behavior that deviated from textbook celestial mechanics. Photometric observations reveal rotation characteristics that suggest a more spherical or moderately elongated form compared to Oumuamua's extreme needle-like proportions. Light curve variations indicate brightness changes of roughly 50% over the rotation period, consistent with an object perhaps twice as long as wide, unusual enough to merit attention but well within the range of shapes observed among asteroids and inactive comet nuclei in our own solar system. This more conventional geometry suggests formation processes similar to those that create typical planetary debris rather than the exotic mechanisms that might explain Oumuamua's extraordinary dimensions. The surface reflectivity of 3I/Atlas falls within the range typical of carbonaceous asteroids and inactive comet nuclei, displaying the dark, reddish coloration characteristic of objects that have experienced extended cosmic ray exposure. Spectroscopic observations reveal absorption features consistent with organic compounds and hydrated minerals, materials commonly found in the outer regions of planetary systems where temperatures remain low enough for complex chemistry to preserve organic molecules and water-bearing phases. These compositional signatures suggest formation in environments similar to the asteroid belt or Kuiper belt regions of alien stellar systems. Perhaps most significantly, 3I/Atlas shows no signs of cometary activity despite receiving solar heating sufficient to sublimate any accessible volatile materials. Unlike Borisov, which developed an obvious coma and tail during its approach to the Sun, this visitor remains completely inert throughout its passage. No gas emission appears in high-resolution spectra, no dust production creates detectable photometric signatures, and thermal observations reveal no evidence of subsurface ice sublimation. The object behaves like a completely desiccated rocky body, despite originating from regions where water ice should have been stable during formation. This absence of volatiles suggests either formation in unusually warm regions of its parent stellar system, or complete processing through mechanisms that removed all accessible ice during the long journey through interstellar space. The former scenario would indicate formation closer to the central star than typical comet-forming regions, perhaps representing debris from terrestrial planet formation rather than outer system materials. The latter possibility implies that cosmic weathering can completely strip volatile materials from objects over timescales of millions of years, transforming originally icy bodies into desiccated rocky remnants. Thermal modeling of 3I/Atlas, based on infrared observations, provides constraints on size, albedo, and thermal inertia that help distinguish between competing formation scenarios. The object appears to measure roughly 200 meters in diameter, making it intermediate in size between Oumuamua and Borisov. Its thermal properties suggest a surface covered by fine regolith or loose aggregate material rather than solid rock, indicating either impact gardening during its interstellar journey or preservation of original accretionary texture from planetary formation processes. The velocity vector and approach direction of 3I/Atlas provide additional clues about its origin and the stellar neighborhood from which it was ejected. Reconstructing the object's trajectory backward through galactic space suggests possible encounters with several nearby stellar systems over the past few million years, though the gravitational perturbations from these encounters make it impossible to identify a specific parent system with certainty. The approach velocity and orbital inclination fall within ranges predicted for objects ejected through gravitational scattering by giant planets in typical stellar systems. Detailed astrometric tracking reveals no evidence of the sublimation-driven jets or asymmetric outgassing that created Oumuamua's mysterious acceleration. 3I/Atlas follows its predicted orbit with precision that matches the best gravitational models, demonstrating that interstellar objects can indeed behave according to conventional celestial mechanics when they lack the exotic properties or hidden volatile reservoirs that complicated the analysis of previous visitors. This predictable behavior enables more precise determinations of orbital parameters and approach trajectories. The discovery of 3I/Atlas coincides with improvements in detection algorithms and survey techniques that allow earlier identification of interstellar visitors, unlike Oumuamua, which was discovered only after closest approach to the Sun. 3I/Atlas is identified while still approaching perihelion, providing astronomers with extended observation windows for detailed study. This earlier detection demonstrates the maturing capabilities of sky survey programs and their increasing efficiency at recognizing the subtle signatures of interstellar origin. Comparison of 3I/Atlas with its predecessors reveals the remarkable diversity that exists among interstellar visitors, even within the small sample of confirmed detections. Each object displays distinctive characteristics that reflect different formation environments, evolutionary pathways, and degrees of modification during interstellar travel. Oumuamua's extreme elongation and mysterious acceleration, Borisov's conventional cometary activity, and 3I/Atlas's inert rocky behavior collectively demonstrate that the population of wandering objects encompasses the full range of materials and structures produced by planetary formation processes. The conventional behavior of 3I/Atlas provides a baseline for understanding how typical interstellar objects should behave under solar system conditions. Its adherence to gravitational mechanics, lack of volatile activity, and familiar surface composition offer reassurance that most future visitors will display characteristics interpretable through established theoretical frameworks. This predictability simplifies mission planning for potential spacecraft encounters and reduces the computational complexity required for orbital tracking and hazard assessment. Spectroscopic analysis of 3I/Atlas reveals subtle differences in elemental abundances and isotopic ratios compared to solar system materials, providing direct evidence for chemical variations between stellar systems. Silicon, magnesium, and iron show abundance patterns that reflect different stellar nucleosynthesis conditions or planetary formation environments, while trace element concentrations suggest exposure to cosmic ray fluxes with different intensities or compositions than those prevalent in our local interstellar neighborhood. The surface properties of 3I/Atlas indicate extensive space weathering that has darkened and reddened the original materials through cosmic ray bombardment and solar wind interactions. These weathering signatures provide information about the radiation environment encountered during the object's interstellar journey, including cosmic ray intensities, magnetic field configurations, and stellar wind conditions that prevailed along its trajectory through galactic space. The degree of weathering suggests exposure timescales consistent with ejection from stellar systems several million years ago, unlike the enigmatic Oumuamua or the familiar Borisov. 3I/Atlas represents what astronomers expect most interstellar visitors to resemble: moderately sized rocky objects that preserve the compositional signatures of their formation while displaying surface modifications consistent with extended exposure to interstellar conditions. This normalcy provides confidence that theoretical models of interstellar object populations accurately predict the characteristics of most wandering materials, even while acknowledging that exceptional objects like Oumuamua occasionally challenge conventional understanding. The analysis of 3I/Atlas benefits from lessons learned during previous interstellar visitor studies, enabling more systematic observations and sophisticated analysis techniques. Coordinated campaigns involving multiple observatories provide comprehensive datasets spanning visible, infrared, and radio wavelengths, while improved computational models allow more precise determination of physical properties and formation constraints. These methodological advances demonstrate the rapid maturation of interstellar object research as a distinct field within planetary science. The spectrum of light reflected from 3I/Atlas carries within its wavelength-dependent variations the chemical fingerprints of materials that condensed from stellar winds and supernova ejecta around another star billions of years ago. Each absorption line and emission feature corresponds to specific atomic transitions that depend on the electronic structure of elements incorporated into minerals during planetary formation. While isotopic ratios preserved in crystalline lattices record the nuclear burning history of the parent star and the galactic chemical evolution that preceded planetary system formation, spectroscopic observations conducted across multiple wavelength ranges reveal composition patterns that differ subtly but measurably from solar system norms. The silicon-to-iron ratio shows variations that suggest formation from material enriched in heavy elements compared to the primordial composition of our own stellar neighborhood. These abundance patterns reflect the stellar nucleosynthesis environment that prevailed when 3I/Atlas's parent star was synthesizing and distributing heavy elements through stellar winds and eventual supernova explosion, processes that occurred under different conditions than those that enriched the pre-solar nebula. High-resolution spectroscopy reveals absorption features associated with pyroxene and olivine minerals that dominate the surface composition, materials commonly found in rocky planets and asteroids throughout our solar system. Yet, the crystal field transitions and vibrational modes of these familiar minerals show subtle shifts that indicate formation under different pressure and temperature conditions than those typical of our inner solar system. The spectral signatures suggest either formation at different distances from the parent star or incorporation of trace elements that modify the electronic structure of common silicate minerals. Thermal infrared observations provide complementary information about surface mineralogy through analysis of fundamental vibrational modes that depend on molecular structure and bonding characteristics. The measured emissivity spectrum reveals features consistent with space-weathered silicate materials similar to those found on primitive asteroids, but with distinctive patterns that indicate exposure to cosmic radiation environments different from those experienced by objects that remained within our solar system. These differences provide insights into the intensity and composition of cosmic ray fluxes encountered during interstellar travel. Perhaps most remarkably, detailed analysis of weak absorption features in the near-infrared spectrum reveals the presence of organic compounds that form through carbon chemistry in the outer regions of an alien stellar system. These molecular signatures indicate complex hydrocarbons and possibly amino acid precursors that condensed from the primordial disk of gas and dust during planetary formation around another star. The preservation of organic materials through millions of years of interstellar exposure demonstrates the resilience of carbon-based chemistry and suggests that the building blocks of biology might be distributed throughout the galaxy through wandering objects like 3Y/Atlas. Isotopic analysis conducted through high-precision spectroscopy reveals deuterium to hydrogen ratios that differ from solar system values, indicating formation from water ice that condensed under different stellar conditions. The measured isotopic signatures suggest incorporation of deuterium-enriched materials that formed in colder regions of the parent stellar system or through chemical processes that operated under different stellar radiation environments. These isotopic variations provide direct evidence for chemical diversity among stellar systems and offer insights into the range of conditions that prevail during planetary formation throughout the galaxy. The oxygen isotopic composition inferred from spectroscopic analysis shows distinctive patterns that reflect the nuclear burning processes operating in the cores of different stellar masses. Stars with masses significantly different from our Sun produce oxygen isotopes in different proportions, creating distinctive signatures that persist in solid materials formed from their ejecta. The measured oxygen isotope ratios in 3E/Atlas provide constraints on the mass and evolutionary state of its parent star, offering insights into stellar populations that existed in other parts of the galaxy when planetary formation was occurring. Trace element abundances determined through detailed spectral analysis reveal the presence of rare Earth elements and refractory metals in concentrations that differ from solar system meteorites. These differences reflect the complex galactic chemical evolution that operated in the stellar neighborhood where 3Y/Atlas formed, including contributions from supernovae of different masses and neutron star mergers that synthesized heavy elements through rapid neutron capture processes. The trace element patterns preserve information about nucleosynthesis events that occurred throughout the formation history of the parent stellar system. The spectral signatures of space weathering products provide additional information about the interstellar environment encountered during 3I/Atlas ESS journey between star systems. Solar wind implantation, cosmic ray bombardment, and micrometeorite impacts have created distinctive surface modifications that alter the original mineral compositions in characteristic ways. Analysis of these weathering products reveals information about the density of interstellar gas, the intensity of cosmic radiation, and the abundance of dust particles along the trajectory followed by this wandering object. Photometric observations conducted in multiple wavelength bands reveal color variations across the surface that suggest heterogeneous composition or differential weathering patterns. These variations might reflect original compositional diversity inherited from the accretionary processes that assembled 3I/Atlas, or they could indicate preferential modification of specific minerals during cosmic ray exposure. The spatial distribution of color variations provides insights into the original texture and structure of materials that formed during planetary accretion in an alien stellar system. Polarimetric measurements of scattered sunlight provide additional constraints on surface texture, particle size distributions, and the optical properties of materials that have been modified by interstellar weathering. The degree and angle of polarization depend on the microscopic structure of surface grains and their aggregation into larger particles through cosmic ray welding and micrometeorite sintering. These measurements reveal information about physical processes that operate on grain scales during extended exposure to the interstellar environment. The comparison of 3I/Atlas spectral properties with laboratory measurements of analog materials helps identify specific mineral phases and their degree of alteration through cosmic processes. Experimental studies of meteorite samples subjected to simulated cosmic ray bombardment and thermal cycling provide calibration for interpreting the spectroscopic signatures observed in interstellar visitors. These laboratory analogies enable quantitative estimates of exposure, ages, and weathering intensities that constrain the duration and conditions of interstellar travel. The spectroscopic analysis also reveals the absence of certain volatile species that might be expected based on formation models for objects originating in the outer regions of planetary systems. The lack of hydrated minerals, carbonate phases, and other water-bearing materials suggests either formation in regions too warm for these phases to be stable or complete dehydration during interstellar exposure. This compositional information constrains formation scenarios and provides insights into the thermal history experienced by wandering objects during their journey through galactic space. Perhaps most significantly, the spectral analysis of 3 I/Atlas demonstrates that each interstellar visitor carries within its composition a unique archive of stellar nucleosynthesis and planetary formation processes that operated under conditions different from those in our solar system. The chemical signatures preserved in reflected sunlight provide direct sampling of alien world-building materials, offering insights into the diversity of planetary formation environments and the range of chemical compositions that characterize solid materials throughout the galaxy. The accumulated spectroscopic evidence suggests that 3 I/Atlas formed from materials that condensed in the outer regions of a stellar system with slightly higher metallicity than our Sun, incorporating trace elements and isotopic signatures that reflect a more chemically evolved stellar environment. The subsequent journey through interstellar space has modified the surface composition through cosmic weathering processes, but the bulk composition preserves the original chemical fingerprints of alien planetary formation. This object represents a direct sample of matter that formed around another star, carrying within its spectral signatures the story of stellar evolution and planetary chemistry that operated billions of years ago in a different part of the galaxy. The wandering objects that occasionally pass through our solar system represent fragments torn from their birth environments during the violent epochs of planetary formation, when gravitational dynamics and catastrophic collisions scattered solid materials across galactic distances like seeds dispersed by cosmic winds. This process of planetary debris ejection operates throughout the galaxy as a fundamental consequence of world building, transforming stellar systems into sources of wandering matter that carry samples of alien chemistry through the darkness between stars for billions of years. During the early phases of planetary system formation, when massive planets migrate through protoplanetary disks and gravitational resonances destabilize previously stable orbits, countless solid objects experience velocity changes sufficient to escape their parent systems entirely. Jupiter-mass planets acting as gravitational slingshots can accelerate smaller bodies to velocities exceeding the escape speed of their stellar systems, launching them into interstellar space with kinetic energies that ensure they will never return to their birth environments. This ejection process operates most efficiently during the first few million years of system evolution, when planetary orbits remain unstable and close encounters between massive bodies frequently disrupt the trajectories of smaller objects. The efficiency of this scattering process depends on the architecture of planetary systems and the masses of their constituent worlds. Systems containing multiple massive planets in unstable configurations can eject substantial fractions of their solid material through gravitational interactions that operate over thousands of orbital periods. Computer simulations suggest that typical planetary systems lose between 10 and 50% of their original solid material to interstellar space through these dynamical processes, creating vast populations of wandering objects that preserve samples of planetary formation conditions from throughout galactic history. Close stellar encounters provide another mechanism for liberating planetary debris from stellar systems and launching it into the galactic environment. When stars pass within a few hundred astronomical units of each other, their gravitational fields can destabilize the outer regions of planetary systems, stripping away comets, asteroids, and even small planets through tidal forces that exceed the binding energy of weakly bound orbits. These stellar encounters occur frequently enough in dense stellar environments to represent a significant source of interstellar wanderers, particularly in regions like stellar clusters where stars regularly approach each other at distances comparable to typical planetary system sizes. The most catastrophic ejection events occur during supernova explosions, when the sudden loss of stellar mass reduces the gravitational binding of all orbiting objects while simultaneously subjecting them to intense radiation pressure and stellar wind interactions. Planets and smaller bodies can acquire velocities of hundreds of kilometers per second during these explosive events, creating populations of high-velocity wanderers that carry distinctive signatures of exposure to supernova shock waves and exotic nuclear processing conditions. These extreme ejection events contribute to the highest velocity components of the interstellar object population while preserving materials that formed under conditions impossible to replicate in stable stellar environments. Planetary collisions during the late heavy bombardment epochs of system evolution create another source of interstellar debris through impact processes that shatter targets into fragments with a wide range of ejection velocities. When massive impactors strike planetary bodies at velocities measured in tens of kilometers per second, the resulting ejector can acquire sufficient velocity to escape not only the target planet but the entire stellar system. These collision-generated fragments preserve samples of differentiated planetary materials, including core metals, mantle silicates, and crustal rocks that form through igneous processes operating on alien worlds. The temporal distribution of ejection events throughout galactic history creates populations of interstellar wanderers with ages spanning billions of years. Objects ejected during the earliest epochs of planetary formation preserve compositional signatures from the galaxy's youth, when stellar metallicities were lower and the abundance patterns of heavy elements differed from contemporary stellar populations. More recent ejecta reflects the chemical evolution of stellar systems and the gradual enrichment of interstellar medium, with heavy elements synthesized in successive generations of massive stars. The size distribution of ejected objects reflects the complex physics of fragmentation and gravitational scattering processes that operate during planetary system evolution. Smaller objects experience more efficient ejection through gravitational encounters, while larger bodies require more energetic processes or multiple scattering events to acquire escape velocities. This size-dependent ejection efficiency creates population distributions that favor smaller wanderers, while ensuring that occasional massive objects also escape into interstellar space, carrying within their substantial masses comprehensive samples of planetary formation materials. The compositional diversity of interstellar wanderers reflects the full range of materials produced during planetary formation processes throughout the galaxy. Objects originating from the inner regions of stellar systems carry signatures of high-temperature condensation and igneous differentiation, while those formed in outer system environments preserve low-temperature ices and organic compounds that remain stable only in cold, radiation-shielded environments. This compositional range encompasses primitive materials that never experience significant thermal processing alongside evolved products of planetary differentiation and surface modification. The velocity distributions of ejected objects depend on the specific mechanisms responsible for their liberation from planetary systems. Gravitational scattering typically produces velocity dispersions of a few kilometers per second relative to the parent star, while more violent processes like stellar encounters or supernova explosions can generate much higher velocities that create distinctive kinematic signatures. These velocity patterns help astronomers identify the likely ejection mechanisms responsible for specific interstellar visitors and constrain the frequency of different types of destabilization events throughout galactic history. The preservation of original formation signatures during interstellar travel depends on the physical properties of ejected objects and the environmental conditions they encounter during their journeys between star systems. Smaller objects with high surface area to volume ratios experience more complete modification through cosmic weathering processes, while larger bodies can preserve primitive compositions in their interiors despite surface alteration. The degree of preservation also depends on the radiation environment and collision frequency along specific trajectories through interstellar space. The accumulation of ejected material in interstellar space over billions of years creates a vast reservoir of planetary samples that represents a form of galactic recycling operating on cosmic timescales. This reservoir contains materials from stellar systems that no longer exist, preserving information about planetary formation conditions that prevailed throughout the galaxy's evolutionary history. The chemical and isotopic signatures carried by these wandering archives provide unique insights into stellar nucleosynthesis, planetary differentiation, and surface modification processes that operated under conditions different from those in our contemporary stellar neighborhood. Perhaps most remarkably, the process of planetary debris ejection operates as a mechanism for distributing complex materials throughout the galaxy, potentially including organic compounds and even microbial life forms that might survive the journey between stellar systems. While the survival of biological materials during million-year transits through interstellar space remains speculative, the demonstrated transport of organic compounds and water-bearing minerals suggests that the building blocks of biology can indeed travel between star systems embedded within rocky or icy carriers that protect them from the harsh radiation environment of interstellar space. The recognition that planetary formation naturally creates vast populations of interstellar wanderers transforms our understanding of galactic ecology from isolated stellar systems to an interconnected network where materials flow between stars over geological timescales. Each ejection event contributes to a galactic scale mixing process that homogenizes chemical compositions and distributes the products of stellar nucleosynthesis throughout the galaxy's disk and halo regions. The chemical analysis of interstellar visitors like Oumuamua, Borisov, and 3I/Atlas provides direct evidence for this cosmic recycling process, revealing compositions that reflect formation in stellar environments with different metallicities, ages, and evolutionary histories than our own solar system. These chemical fingerprints demonstrate that the galaxy operates as a vast laboratory where planetary formation experiments conducted around different types of stars contribute samples to a shared archive of cosmic evolution preserved in wandering objects drifting through interstellar space. The timescales involved in this recycling process span the entire history of galaxy formation and stellar evolution. Objects ejected during the earliest epochs of planetary formation, when the galaxy contained primarily first-generation stars with low heavy element abundances, continue to wander through space carrying primitive compositions that reflect conditions during the galaxy's youth. These ancient wanderers serve as time capsules that preserve information about chemical conditions that existed billions of years before our solar system formed. More recent contributions to the interstellar population reflect the gradual chemical enrichment of the galaxy through successive generations of stellar evolution. Objects ejected from second- and third-generation stellar systems carry higher metallicities and more complex chemical signatures that document the progressive synthesis of heavy elements through supernova explosions and stellar wind mass loss. This temporal stratification creates a population of wanderers whose compositions span the entire range of galactic chemical evolution. The spatial distribution of interstellar objects throughout the galaxy reflects the complex dynamics of stellar motion and galactic rotation that transport ejected materials far from their origins over millions of years. Objects ejected from stars in the galactic bulge gradually migrate outward through gravitational interactions and spiral density wave perturbations, while material from outer disk regions can be scattered inward toward the galactic center through similar processes. This radial mixing ensures that samples from diverse galactic environments eventually disperse throughout the galaxy's volume. The vertical distribution of wandering objects above and below the galactic plane depends on the velocity dispersions acquired during ejection and the subsequent gravitational interactions that modify their orbits over time. High-velocity ejecta from supernova explosions or close stellar encounters can achieve sufficient energy to escape the galactic disk entirely, populating the halo regions with samples of disk chemistry that provide information about stellar populations and chemical evolution in regions where direct observation of ancient stellar systems becomes impossible. The preservation of formation signatures within interstellar wanderers depends on their internal structure and the degree of protection afforded to primitive materials by radiation-resistant outer layers. Large objects can maintain temperature and pressure conditions in their cores that preserve original mineralogy and chemical compositions despite millions of years of cosmic ray bombardment and thermal cycling. These protected interiors serve as repositories for information about planetary formation processes, igneous differentiation, and aqueous alteration that operated under alien conditions around other stars. The study of interstellar visitors, therefore, provides a unique window into planetary formation processes operating throughout the galaxy, under conditions that range far beyond those accessible through observations of our own solar system. Each wanderer carries within its composition and structure the integrated history of stellar nucleosynthesis, planetary accretion, and subsequent evolution that occurred in stellar environments with different masses, metallicities, and evolutionary states than our Sun. This diversity reveals the range of physical and chemical conditions that characterize planetary formation throughout the galaxy. The implications extend beyond planetary science to fundamental questions about the prevalence and characteristics of habitable worlds throughout the galaxy. If interstellar wanderers preserve samples of surface materials from alien planets, including organic compounds and water-bearing minerals that form through processes relevant to biological evolution, then their study might provide insights into the chemical conditions that exist on potentially habitable worlds orbiting other stars. The detection of complex organic chemistry in interstellar visitors would suggest that the building blocks of biology form readily under diverse stellar conditions. The future study of interstellar objects promises to transform our understanding of cosmic evolution from a theoretical enterprise based on distant observations to an empirical science based on direct laboratory analysis of alien materials. As detection rates increase and analytical techniques improve, astronomers will gain access to comprehensive samples of planetary formation products from throughout the galaxy, creating an unprecedented database of cosmic chemistry that spans billions of years of galactic evolution and stellar system formation. Each interstellar visitor that tumbles through our solar system carries within its weathered surface and ancient interior the accumulated testimony of stellar processes and planetary formation mechanisms that operated under conditions fundamentally different from those that shaped our local cosmic neighborhood. These wandering archives preserve direct samples of materials that condensed from stellar winds, incorporated supernova ejecta, and experienced planetary differentiation around stars with masses, metallicities, and evolutionary histories distinct from our Sun, offering unprecedented opportunities to study comparative planetary science on a galactic scale. The chemical compositions revealed through spectroscopic analysis of visitors like 3Y/Atlas provide quantitative constraints on stellar nucleosynthesis processes that operated in different parts of the galaxy during various epochs of cosmic evolution. Isotopic ratios preserved in crystalline minerals record the neutron flux conditions that existed in stellar cores during heavy element synthesis, while trace element abundances reflect the complex nuclear reaction networks that created elements heavier than iron through slow and rapid neutron capture processes. These signatures allow astronomers to reconstruct the stellar environment and evolutionary state of parent stars that existed billions of years ago in stellar neighborhoods now dispersed throughout the galaxy. The mineralogical diversity observed in interstellar objects reveals the range of pressure, temperature, and chemical conditions that prevailed during planetary formation around different stellar types. High-pressure phases that form only under extreme conditions provide evidence for impact processing or deep burial within large planetary bodies, while low-temperature minerals indicate formation in cold outer regions where volatile compounds remain stable over geological timescales. The coexistence of materials formed under disparate conditions within single objects suggests complex accretionary histories that involved mixing of components from different radial zones of alien stellar systems. Organic compounds detected in the spectra of some interstellar visitors provide direct evidence for carbon chemistry operating in extraterrestrial environments, demonstrating that the molecular building blocks of biological processes form readily under diverse stellar conditions. The complexity and diversity of organic molecules preserved in these ancient samples indicate that carbon-based chemistry operates as a universal phenomenon throughout the galaxy, creating complex molecular inventories that might serve as precursors to biological evolution on worlds orbiting other stars. The survival of organic materials through millions of years of interstellar exposure suggests remarkable stability under cosmic conditions. The preservation of hydrated minerals and other water-bearing phases in some interstellar objects provides insights into aqueous alteration processes that operated on alien worlds under hydrological conditions different from those on Earth. The specific hydrated phases present depend on temperature, pressure, pH, and dissolved ion concentrations that characterize aqueous environments, while their spatial distribution within individual objects reveals information about fluid flow patterns and chemical gradients that existed during alteration. These aqueous signatures offer direct evidence for water-rock interactions that might have created habitable environments on planets orbiting other stars. The metamorphic textures and shock features preserved in some interstellar fragments provide evidence for high-energy processes that operated during planetary formation and evolution around other stars. Impact crater formation. Volcanism and tectonic activity create distinctive mineralogical signatures that survive millions of years of interstellar weathering, allowing reconstruction of geological processes that shaped alien worlds. The intensity and frequency of these processes can be inferred from the degree of shock, metamorphism, and thermal alteration preserved in wandering samples. The size distributions and internal structures revealed through detailed observations of interstellar visitors constrain the fragmentation and ejection mechanisms that liberated these objects from their parent systems. The presence of coherent crystalline structures indicates that ejection occurred through relatively gentle processes that preserved original accretionary textures, while brecciated or heavily fractured materials suggest more violent liberation through catastrophic impacts or explosive events. These structural signatures help distinguish between different ejection scenarios and provide insights into the dynamical evolution of alien planetary systems. The cosmic ray exposure signatures recorded in the surface layers of interstellar objects provide unique information about the radiation environment and magnetic field structure of interstellar space along specific trajectories through the galaxy. The depth distribution of radiation damage, the abundance of spallation products, and the degree of surface modification collectively constrain the intensity and composition of cosmic ray fluxes encountered during interstellar travel. These measurements complement direct observations of cosmic ray physics and provide insights into the galactic magnetic field configurations that influence particle propagation. The thermal evolution signatures preserved in interstellar visitors reveal information about heating and cooling processes that operated during their formation and subsequent modification. Thermal metamorphism, igneous differentiation, and impact melting create distinctive textural and chemical signatures that persist despite surface weathering during interstellar exposure. The degree of thermal processing indicates the size and internal structure of parent bodies, while cooling rates constrain the efficiency of heat loss mechanisms and the duration of thermal events. The comparison of interstellar visitor compositions with solar system meteorites reveals both similarities and differences that illuminate universal versus system-specific aspects of planetary formation. Elements and compounds that appear consistently across different stellar systems indicate universal chemical processes operating under similar physical conditions, while systematic variations reveal the influence of stellar mass, metallicity, and evolutionary state on planetary chemistry. These comparisons provide empirical constraints on theoretical models of planetary formation and chemical evolution. The temporal variations in the properties of interstellar visitors detected over multiple years provide insights into the spatial and temporal distribution of ejected materials throughout the galaxy. Objects arriving from different directions carry information about stellar populations and chemical evolution in various galactic regions, while the time sequence of detections samples the local density and velocity distribution of the wandering population. These observational patterns reveal large-scale structure in the distribution of interstellar objects and constrain models of galactic chemical evolution. The discovery that each interstellar visitor provides unique insights into alien world-building processes transforms these objects from curiosities into essential tools for understanding planetary formation throughout the galaxy. Rather than representing mere samples of alien materials, these wandering archives preserve comprehensive records of stellar nucleosynthesis, planetary accretion, geological evolution, and chemical processing that operated under conditions spanning the full range of stellar environments. Each new detection adds another piece to the growing puzzle of cosmic evolution and planetary diversity. The implications extend beyond planetary science to fundamental questions about the universality of physical and chemical processes throughout the cosmos. If the same basic mechanisms operate in stellar systems with vastly different characteristics, then the principles governing planetary formation represent universal laws that constrain the types of worlds that can form around any star. Conversely, if systematic variations exist between different stellar environments, then the diversity of planetary systems might exceed current theoretical expectations, suggesting that habitable worlds could emerge under conditions very different from those that prevailed during Earth's formation. The accumulating database of interstellar visitor properties provides empirical constraints on theories of planetary formation, stellar evolution, and galactic chemical evolution that complement but cannot be replaced by observations of distant exoplanetary systems. While telescopic surveys can detect and characterize planets orbiting other stars, only direct analysis of materials from those systems can provide the detailed chemical and physical information necessary to understand the processes that shaped their formation and evolution. Interstellar visitors bridge the gap between remote sensing and laboratory analysis, bringing samples of alien worlds within reach of terrestrial instruments. Perhaps most remarkably, the study of these cosmic messengers reveals that the galaxy operates as a vast, interconnected system where materials and information flow between stellar systems over timescales measured in millions of years. Each wandering object represents a message written in the universal language of chemistry and physics, carrying news from distant worlds across the emptiness between stars to whatever civilization happens to be watching when they finally arrive. The universe, it seems, shares its secrets more generously than anyone imagined, delivering samples of its cosmic experiments one ancient fragment at a time. The next generation of astronomical surveys promises to transform the study of interstellar visitors from individual case studies of rare objects into systematic statistical analysis of a substantial population, revealing patterns and correlations that illuminate the large-scale processes governing planetary formation throughout the galaxy. Advanced ground-based telescopes and space-based observatories, now under development, will detect dozens of interstellar objects each year, building comprehensive databases that enable population studies impossible with the handful of visitors discovered during astronomy's first tentative steps into this new field. The Vera Rubin Observatory's Legacy Survey of Space and Time represents the most significant near-term advance in interstellar object detection capabilities, promising to increase discovery rates by orders of magnitude through its unprecedented combination of wide field coverage, deep sensitivity, and rapid cadence observations. The facility's 10-year survey will repeatedly image the entire visible sky every few nights, creating a comprehensive motion picture of the solar system that captures interstellar visitors from their first appearance until they fade beyond detection limits. Computer models predict that this survey alone will detect several hundred interstellar objects during its operational lifetime. The European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will contribute space-based observations that complement ground-based surveys through their ability to observe continuously without atmospheric interference or day-night cycles. These facilities can track faint objects for extended periods while providing precise astrometry that enables accurate orbit determination and physical characterization. The combination of ground and space-based observations will create unprecedented datasets for studying interstellar visitor populations and their statistical properties. Advanced detection algorithms incorporating machine learning techniques will automatically identify candidate interstellar objects from the vast streams of observational data generated by next-generation surveys. These systems will recognize the subtle orbital signatures that distinguish visitors from native solar system objects while minimizing false positive rates that could overwhelm follow-up observation capabilities. Neural networks trained on synthetic populations of interstellar objects will identify promising candidates within hours of initial detection, enabling rapid confirmation and detailed study before objects fade beyond reach. The development of specialized rapid response observational capabilities will maximize the scientific return from each detected visitor through coordinated campaigns involving multiple telescopes and instruments. Automated alert systems will immediately notify observatories worldwide when new interstellar objects are confirmed, triggering pre-planned observational sequences that optimize the use of available telescope time. These campaigns will gather comprehensive datasets spanning multiple wavelength ranges, while objects remain bright enough for detailed spectroscopic and photometric analysis. Future space missions dedicated to interstellar object science may attempt close proximity encounters or sample return from particularly interesting visitors, providing detailed physical and chemical analysis impossible through remote sensing alone. Conceptual mission designs envision spacecraft that remain dormant in solar orbit until awakened by the discovery of suitable targets, then execute rapid intercept trajectories that bring instruments within hundreds of kilometers of passing objects. Such missions would represent humanity's first direct exploration of materials from alien stellar systems. The statistical analysis of large interstellar visitor populations will reveal correlations between physical properties, compositional characteristics, and orbital parameters that constrain formation and ejection mechanisms operating throughout the galaxy. Size distributions will illuminate fragmentation processes and ejection efficiency as functions of parent body characteristics, while compositional surveys will reveal chemical variations that reflect different stellar environments and evolutionary histories. These population studies will transform theoretical models of planetary formation from solar system-specific paradigms to universal frameworks applicable throughout the galaxy. Velocity distribution analysis will provide insights into the ejection mechanisms responsible for liberating objects from their parent systems and the subsequent gravitational interactions that modify their trajectories during interstellar travel. Objects ejected through gentle gravitational scattering will display different velocity characteristics than those accelerated by violent processes like supernova explosions or close stellar encounters. The measured velocity distributions will constrain the relative importance of different ejection mechanisms and their variation with stellar mass, metallicity, and galactic environment. Compositional surveys of interstellar visitor populations will reveal the chemical diversity of planetary formation throughout the galaxy while identifying systematic variations that reflect stellar nucleosynthesis and galactic chemical evolution. Objects originating from metal-poor stellar systems in the galactic halo will display different elemental abundances than those formed around metal-rich disk stars, creating a chemical taxonomy that maps galactic structure and evolution through direct sampling of planetary materials. These compositional patterns will provide empirical constraints on models of stellar evolution and galactic chemical enrichment. The temporal distribution of interstellar visitor discoveries will sample the velocity and spatial structure of the local wandering population while revealing seasonal and directional variations that reflect the solar system's motion through galactic space. Objects approaching from the direction of solar motion will arrive with systematically different relative velocities than those encountered from other directions, creating observable patterns that constrain the kinematic structure of the local stellar neighborhood and the distribution of ejected materials throughout nearby space. Size-dependent detection biases will be carefully characterized and corrected through detailed modeling of observational selection effects, enabling accurate determination of the intrinsic size distribution of interstellar objects. Smaller objects remain detectable only when they approach closer to the Sun or possess unusually high reflectivities, while larger bodies can be observed at greater distances and for longer periods. Understanding these selection effects becomes crucial for interpreting population statistics and comparing observed distributions with theoretical predictions. The development of standardized observational protocols and data reduction techniques will ensure that measurements from different facilities can be combined into coherent databases suitable for statistical analysis. Photometric systems, spectroscopic calibrations, and astrometric reference frames must be carefully coordinated between observatories to enable meaningful comparisons of measurements obtained under different observational conditions. These standardization efforts will maximize the scientific value of distributed observational campaigns. Advanced theoretical modeling will interpret observed population characteristics in terms of the underlying physical processes responsible for interstellar object formation, ejection, and modification during galactic travel. Monte Carlo simulations incorporating realistic models of planetary formation, dynamical evolution, and cosmic weathering will generate synthetic populations that can be compared directly with observational data. These comparisons will test theoretical frameworks and identify areas where current understanding requires revision or refinement. The integration of interstellar object studies with broader astronomical research programs will reveal connections between planetary formation, stellar evolution, and galactic structure that remain invisible when these phenomena are studied in isolation. Correlations between local stellar populations and interstellar visitor characteristics will illuminate the relationship between stellar properties and planetary system architectures, while temporal variations in discovery rates may reflect the solar system's passage through different galactic environments during its orbit around the galactic center. Perhaps most significantly, the systematic study of interstellar visitor populations will establish empirical foundations for understanding planetary formation as a galactic phenomenon rather than a process unique to individual stellar systems. The recognition that planetary formation operates according to universal physical laws modified by local stellar conditions will provide crucial insights for interpreting observations of exoplanetary systems and assessing the likelihood of finding habitable worlds orbiting other stars. Each wandering fragment becomes a piece of evidence in humanity's growing understanding of cosmic evolution and our place within the vast community of worlds that populate the galaxy. The realization that interstellar objects preserve information spanning billions of years of galactic evolution transforms these wandering fragments into cosmic time capsules that carry within their compositions and structures the accumulated history of stellar nucleosynthesis, planetary formation, and chemical processing that operated throughout the galaxy's past. Each visitor represents a direct sample from specific epochs in cosmic history, preserving materials that formed under stellar conditions that existed billions of years ago when the galaxy contained different stellar populations and chemical abundances than those observed today. The chronological information encoded within interstellar visitors operates on multiple timescales that span from the nuclear burning processes that created their constituent elements to the recent cosmic ray exposure that modified their surfaces during interstellar travel. Radiometric dating techniques applied to these materials could potentially reveal formation ages that extend back to the earliest epochs of planetary formation in the galaxy. Providing direct evidence for the timescales and conditions that characterized world-building processes during the galaxy's youth, when stellar metallicities remained low and planetary formation occurred under chemical conditions very different from contemporary stellar environments. The isotopic compositions preserved in crystalline minerals carry detailed records of the nuclear reaction networks that operated in stellar cores during heavy element synthesis, including information about neutron flux intensities, stellar masses, and burning timescales that characterized the parent stars. These nuclear signatures persist unchanged despite millions of years of interstellar weathering, providing direct access to stellar physics data from stars that completed their evolution billions of years ago and no longer exist as observable objects in the contemporary galaxy. The metamorphic and igneous textures preserved within some interstellar fragments record thermal histories that reflect planetary differentiation processes operating on alien worlds during various stages of their geological evolution. Cooling rates inferred from crystal sizes and chemical zoning patterns reveal information about planetary structure, heat transport mechanisms, and the duration of igneous activity that shaped rocky worlds orbiting other stars. These thermal signatures provide unique insights into planetary evolution processes that remain invisible through telescopic observations of distant exoplanetary systems. The organic compounds detected in some interstellar visitors preserve chemical information about carbon-based molecular synthesis that occurred in circumstellar environments or on planetary surfaces around other stars. The complexity and molecular weight distributions of these organic materials reflect the chemical conditions, energy sources, and reaction timescales that characterized organic synthesis in alien environments. The preservation of these delicate molecules through millions of years of cosmic exposure demonstrates remarkable chemical stability under interstellar conditions. The shock metamorphic features and impact signatures found in some interstellar objects record catastrophic events that occurred during planetary formation or subsequent geological evolution around other stars. The pressure and temperature conditions inferred from shock minerals provide quantitative constraints on impact velocities, crater formation processes, and the intensity of bombardment episodes that shaped alien worlds. These signatures offer direct evidence for violent processes that operated during planetary evolution in stellar systems throughout the galaxy. The cosmic ray exposure signatures accumulated during interstellar travel create detailed records of the radiation environment and magnetic field structure encountered along specific trajectories through galactic space. The depth distribution of radiation damage and the abundance of spallation products provide information about cosmic ray intensities, energy spectra, and compositional variations that characterized different regions of the galaxy during the past several million years. These measurements complement astronomical observations of cosmic ray physics and galactic magnetic field structure. The surface weathering patterns and chemical alteration signatures created during extended exposure to interstellar conditions preserve information about the physical and chemical environment of interstellar space along the wandering paths followed by these objects. The degree of space weathering depends on the density of interstellar gas, the flux of cosmic rays, and the abundance of dust particles encountered during travel between stellar systems. These weathering signatures provide unique probes of interstellar medium properties that supplement direct astronomical observations. The thermal evolution histories recorded in mineral assemblages and textural relationships reveal information about heating and cooling processes that operated during planetary formation and subsequent modification around other stars. Phase equilibria and reaction kinetics preserved in crystalline structures constrain temperature-time paths that characterized igneous differentiation, metamorphic recrystallization, and hydrothermal alteration under alien planetary conditions. These thermal signatures provide direct evidence for geological processes operating on worlds orbiting other stars. The mechanical properties and structural characteristics of interstellar fragments preserve information about the physical processes that shaped their formation and ejection from parent bodies. Fracture patterns, grain size distributions, and porosity structures record impact events, explosive fragmentation, and gravitational disruption that liberated these objects from their original stellar systems. The preservation of these mechanical signatures constrains ejection mechanisms and provides insights into the dynamical evolution of alien planetary systems. The chemical gradients and compositional zoning patterns preserved within individual interstellar objects record accretionary processes and subsequent chemical evolution that occurred during planetary formation around other stars. Trace element distributions and mineral phase relationships reveal information about mixing timescales, temperature gradients, and chemical transport mechanisms that characterized planetary accretion under diverse stellar conditions. These chemical patterns provide unique constraints on planetary formation theories and their universal applicability. The magnetic signatures and paleomagnetic records potentially preserved in some interstellar fragments could provide information about magnetic field strengths and orientations that characterized alien planetary environments during their geological evolution. Remnant magnetization patterns record ancient magnetic field conditions while constraining dynamo processes and magnetic field evolution on worlds orbiting other stars. These magnetic signatures offer insights into planetary interior dynamics and atmospheric evolution under diverse stellar conditions. Perhaps most remarkably, the collective information preserved within the growing population of interstellar visitors creates an unprecedented archive of galactic evolution that spans billions of years of cosmic history. Each object contributes unique data points to a comprehensive database of stellar nucleosynthesis, planetary formation, and chemical evolution that operated throughout the galaxy's past. This archive provides direct empirical constraints on theoretical models of cosmic evolution while revealing the diversity and universality of physical processes operating throughout the galaxy. The temporal stratification within this archive reflects the complex history of galactic chemical evolution and stellar population synthesis that transformed the galaxy from its initial state of primordial hydrogen and helium to the chemically diverse environment observed today. Objects formed during different epochs preserve compositional signatures that document the gradual enrichment of interstellar medium with heavy elements through successive generations of stellar evolution and supernova nucleosynthesis. The spatial sampling provided by interstellar visitors reveals chemical and physical variations that characterize different regions of the galaxy during various epochs in cosmic history. Objects originating from the galactic bulge, spiral arms, and halo regions carry distinctive signatures that reflect the diverse stellar populations and chemical evolution histories that characterize these different galactic environments. This spatial sampling provides unique insights into galactic structure and evolution that complement but cannot be replaced by telescopic observations. The recognition that interstellar objects function as messages written in stone and ice by the galaxy itself transforms their study from simple planetary science to a form of galactic archaeology that decodes billions of years of cosmic evolution through direct laboratory analysis of alien materials. Each visitor delivers a carefully preserved sample of conditions that existed somewhere in the galaxy at some time in cosmic history, contributing to humanity's growing understanding of the vast and ancient processes that shaped the chemical and physical evolution of the universe itself. The systematic preparation for studying future interstellar visitors requires a coordinated transformation of astronomical infrastructure that encompasses detection capabilities, rapid response protocols, and analytical techniques specifically optimized for these fleeting cosmic messengers. The lessons learned from Oumuamua, Borisov, and 3I/Atlas have revealed both the enormous scientific potential and the significant observational challenges posed by objects that remain detectable for only weeks or months before fading back into the darkness between stars. Advanced survey telescopes currently under construction will incorporate design features specifically intended to maximize interstellar object detection rates through optimized field coverage, sensitivity thresholds, and observational cadences. The Vera Rubin Observatory's sophisticated scheduling algorithms will automatically adjust observational priorities to provide additional coverage of sky regions where interstellar visitors have been detected, while maintaining the systematic survey patterns necessary for comprehensive population studies. These adaptive observing strategies will balance the competing demands of systematic discovery with intensive follow-up observations. The development of specialized rapid response instrumentation represents a critical component in maximizing the scientific return from each detected interstellar visitor. New spectrographs optimized for faint, fast-moving targets will incorporate advanced detector technologies and efficient optical designs that enable compositional analysis of objects near the detection limits of major telescopes. These instruments will provide broader wavelength coverage and higher sensitivity than general-purpose spectrographs, enabling detailed analysis of absorption features and emission lines that characterize alien materials. Automated alert systems will coordinate observations across multiple facilities through sophisticated communication networks that immediately notify relevant telescopes when new interstellar objects are confirmed. These systems will incorporate artificial intelligence algorithms that automatically prioritize targets based on their scientific importance, observational accessibility, and the remaining time available for detailed study. The integration of space-based and ground-based facilities will provide continuous monitoring capabilities that overcome the limitations imposed by weather, daylight, and atmospheric conditions. Laboratory preparation for analyzing interstellar materials will require advances in analytical techniques that can extract maximum information from the limited datasets available through remote sensing observations. New spectroscopic databases will catalog the signatures of exotic minerals and organic compounds that might exist under alien formation conditions, while experimental studies will investigate how cosmic weathering processes modify familiar materials during extended exposure to interstellar environments. These laboratory foundations will enable more sophisticated interpretation of observational data. Mission planning for potential spacecraft encounters with interstellar visitors will require innovative approaches to trajectory, design, and instrument deployment that can respond to targets identified with minimal advance warning. Conceptual mission architectures envision pre-positioned spacecraft that remain dormant in heliocentric orbits until activated by the discovery of suitable targets, then execute rapid intercept maneuvers that bring scientific instruments within close proximity of passing objects. These missions will require autonomous navigation systems and robust communication links that operate reliably during high-speed encounters. The development of standardized observational protocols will ensure that data collected by different facilities can be combined into coherent datasets suitable for population studies and comparative analysis. Photometric systems will be carefully calibrated to enable accurate brightness measurements across different telescopes and observational conditions, while spectroscopic standards will provide consistent wavelength calibration and instrumental response corrections. These standardization efforts will maximize the scientific value of distributed observational campaigns conducted under time-critical conditions. Theoretical modeling capabilities will expand to include sophisticated simulations of interstellar object formation, ejection, and evolution that can predict the observable characteristics of future visitors based on their formation environments and travel histories. These models will incorporate realistic treatments of cosmic weathering processes, thermal evolution, and mechanical modification during interstellar exposure, enabling more accurate interpretation of observational data and better planning for future observational campaigns. International cooperation will become increasingly important as the detection rate of interstellar visitors increases and the need for coordinated follow-up observations exceeds the capabilities of individual observatories or national research programs. Formal agreements between major observatories will establish protocols for sharing telescope time and coordinating observations during interstellar object events, while data sharing agreements will ensure that scientific results benefit the entire international research community. Educational and public outreach programs will prepare the broader scientific community and general public for the increasing frequency of interstellar visitor discoveries by providing background information about their scientific significance and the observational techniques used to study them. Training programs for graduate students and postdoctoral researchers will develop expertise in the specialized analytical methods required for interstellar object research, while public communications will maintain enthusiasm and support for continued investment in survey telescopes and follow-up capabilities. Advanced computational infrastructure will be required to process the enormous datasets generated by next-generation survey telescopes, and to identify interstellar visitor candidates among the millions of moving objects detected each night. High-performance computing clusters will run sophisticated orbit determination algorithms that can distinguish hyperbolic trajectories from highly eccentric elliptical orbits, while machine learning systems will recognize subtle patterns in observational data that indicate interstellar origin. The preparation of sample analysis protocols will establish procedures for future missions that might return physical samples from interstellar visitors, including contamination control measures, analytical sequences, and preservation techniques that maintain the integrity of alien materials during transport and laboratory study. These protocols will draw upon experience gained from asteroid and comet sample return missions while adapting to the unique challenges posed by materials that formed under unknown conditions around other stars. Quality assurance procedures will ensure that observational measurements and analytical results meet the rigorous standards necessary for scientific publication and theoretical interpretation. Independent verification of critical measurements will be conducted by multiple research groups using different telescopes and analytical techniques, while systematic error analysis will identify and correct potential biases that could compromise scientific conclusions. These quality control measures will maintain the credibility of interstellar object research as it transitions from individual case studies to systematic population analysis. The integration of interstellar object research with broader astronomical research programs will reveal connections between planetary formation, stellar evolution, and galactic structure that remain invisible when these phenomena are studied in isolation. Coordinated observations will simultaneously characterize interstellar visitors and the stellar populations in their approach directions, while theoretical studies will explore correlations between local galactic properties and the characteristics of detected objects. Perhaps most importantly, the systematic preparation for future interstellar visitor studies will establish the observational and analytical infrastructure necessary to transform these chance encounters into a routine component of astronomical research. The recognition that the galaxy delivers samples of alien worlds with predictable frequency will enable long-term research programs that build comprehensive databases of interstellar object properties while developing increasingly sophisticated techniques for extracting information about planetary formation throughout the cosmos. The patient architecture of discovery will reveal its rewards to those who prepare carefully and observe systematically. transforming the study of interstellar visitors from an opportunistic science based on serendipitous discoveries to a mature field with dedicated facilities. Standardized methods and theoretical frameworks capable of addressing fundamental questions about planetary formation and cosmic evolution. Each visitor will contribute to humanity's growing understanding of the vast population of worlds that populate the galaxy, carrying messages written in the universal language of chemistry and physics across the emptiness between stars. The quiet revolution in astronomy unfolds not through dramatic announcements or paradigm-shifting discoveries, but through the patient accumulation of data from cosmic messengers that arrive unannounced from the depths of interstellar space, each carrying within its ancient composition and weathered structure direct samples of alien world-building processes that operated under conditions spanning the full diversity of stellar environments throughout galactic history. This transformation occurs almost imperceptibly as the detection of interstellar visitors transitions from extraordinary events that capture headlines to routine observations that provide systematic sampling of planetary formation throughout the galaxy. The methodical expansion of survey capabilities and analytical techniques creates an infrastructure capable of detecting, tracking, and characterizing dozens of interstellar objects each year, building comprehensive databases that reveal population statistics and compositional patterns impossible to discern from individual case studies. Each new detection adds another data point to the growing census of alien materials, while testing theoretical models of planetary formation against empirical evidence gathered from throughout the galaxy. The accumulation of these measurements creates a foundation for understanding planetary science as a universal phenomenon rather than a process unique to individual stellar systems. The recognition that interstellar space contains vast populations of wandering objects fundamentally alters humanity's perception of the galaxy from a collection of isolated stellar systems to an interconnected ecosystem where materials flow between stars over timescales measured in millions of years. This perspective transforms planetary formation from a local process confined to individual stellar systems into a galactic phenomenon that operates according to universal physical laws while displaying variations that reflect the diverse conditions characterizing different stellar environments and evolutionary epochs. The systematic study of interstellar visitor compositions reveals chemical signatures that document the full range of stellar nucleosynthesis processes operating throughout galactic history. From the metal-poor conditions that characterized early stellar generations to the chemically enriched environments surrounding contemporary stars, these compositional patterns provide direct empirical constraints on models of galactic chemical evolution, while revealing the relationship between stellar properties and the characteristics of planetary materials formed in their gravitational domains. The temporal sampling provided by objects with different cosmic ray exposure ages creates a chronological sequence that spans millions of years of galactic evolution, revealing variations in interstellar conditions, stellar populations, and chemical abundances that occurred as the solar system moved through different regions of galactic space. This temporal perspective provides unique insights into local galactic structure and evolution that complement but cannot be replaced by observations of distant stellar populations and their associated planetary systems. The diversity of physical properties observed among interstellar visitors illuminates the range of formation and evolutionary processes that shape solid materials throughout the galaxy. From primitive objects that preserve original accretionary textures to highly processed fragments that experienced extensive thermal metamorphism and impact modification on alien worlds. This diversity demonstrates that planetary formation operates under a wide range of conditions while producing materials recognizable through their chemical and physical signatures. The mechanical simplicity of studying actual samples rather than interpreting electromagnetic radiation across vast distances provides unprecedented access to detailed information about atomic-scale processes, crystalline structures, and chemical relationships that remain invisible through telescopic observations. Each grain of cosmic dust and crystalline fragment preserves information about formation conditions, thermal histories, and chemical evolution that would require centuries of telescopic observations to infer indirectly from distant planetary systems. The democratization of cosmic exploration through the natural delivery of alien samples eliminates the enormous costs and technical challenges associated with interstellar space missions while providing access to materials from stellar systems distributed throughout the local galactic neighborhood. Rather than requiring decades of technological development and enormous financial investments to reach other stars, humanity receives samples of alien worlds through the patient operation of natural processes that have transported these materials across interstellar distances over geological timescales. The philosophical implications extend beyond scientific research to fundamental questions about humanity's relationship with the cosmos and our membership in a galactic community of worlds connected through the exchange of materials over vast distances and timescales. The recognition that we regularly receive visitors from other stellar systems establishes direct physical connections between our planet and the broader galactic environment while demonstrating that the universe operates as an integrated system where information and materials flow between widely separated regions. The transformation of astronomy from a purely observational science to one that incorporates direct laboratory analysis of cosmic materials represents a methodological revolution that promises to accelerate discovery and deepen understanding across multiple fields of research. The combination of traditional astronomical observations with sophisticated laboratory techniques creates powerful synergies that reveal information about cosmic processes operating on scales from atomic nuclei to galactic structure. The establishment of interstellar object research as a routine component of astronomical investigation creates opportunities for systematic progress on fundamental questions about planetary formation, stellar evolution, and galactic structure that previously remained accessible only through theoretical modeling and indirect observations. The regular delivery of alien samples enables hypothesis testing and model validation through direct empirical evidence rather than statistical inference from distant observations. The integration of interstellar object studies with broader research programs in astrobiology, exoplanet science, and galactic astronomy creates intellectual connections that illuminate the relationships between stellar properties, planetary formation, and the potential for biological evolution throughout the galaxy. Each wandering fragment provides constraints on the chemical conditions and physical processes that characterize planetary environments around different stellar types, while revealing the prevalence of organic compounds and water-bearing minerals that might support biological evolution. The accumulating evidence that the galaxy naturally distributes complex materials between stellar systems over geological timescales suggests mechanisms for chemical and potentially biological exchange that operate on cosmic scales far beyond the reach of any conceivable technological civilization. This natural panspermia operates through the transport of organic compounds, water-bearing minerals, and potentially viable microorganisms embedded within rocky or icy carriers that protect them from the harsh radiation environment of interstellar space during million-year journeys between stellar systems. The recognition that human civilization has emerged during an epoch when technological capabilities finally enable detection and analysis of interstellar visitors creates a profound sense of cosmic timing and opportunity. For billions of years, these messengers have passed through the solar system unnoticed, their scientific treasures remaining invisible to any observers who might have existed on Earth during previous geological epochs. Only now, during the brief historical moment when telescopes possess sufficient sensitivity and analytical techniques have achieved adequate sophistication, can humanity begin to decode the messages written in stone and ice by the galaxy itself? The patient operation of natural processes over cosmic timescales delivers to human civilization a comprehensive sampling of planetary formation throughout the local galactic neighborhood, while providing direct access to materials from stellar systems that existed billions of years ago under chemical and physical conditions very different from contemporary galactic environments. This natural archive preserves information about cosmic evolution that remains accessible through no other means, creating opportunities for scientific discovery that will continue expanding as detection capabilities improve and analytical techniques advance. The transformation of these chance encounters into systematic science requires sustained commitment to long-term observational programs, technological development, and international cooperation that transcends the typical timescales of scientific funding cycles and political administrations. The full scientific potential of interstellar visitor research will be realized only through decades of patient observation and analysis that build comprehensive databases while developing increasingly sophisticated techniques for extracting information from fleeting encounters with ancient cosmic materials. The establishment of theoretical frameworks capable of interpreting the growing database of interstellar object properties represents an intellectual challenge that requires synthesis of knowledge from stellar evolution, planetary formation, galactic dynamics, and cosmic chemistry. These theoretical advances will enable prediction of visitor characteristics based on their formation environments while providing guidance for optimizing observational strategies and analytical techniques. The development of computational tools capable of processing the enormous datasets generated by systematic surveys while identifying subtle patterns and correlations that reveal underlying physical relationships creates opportunities for discovery through data mining and machine learning techniques applied to astronomical problems. These computational approaches will become increasingly important as detection rates exceed human capacity for individual analysis of each visitor. The training of new generations of researchers with expertise spanning traditional astronomy, planetary science, and laboratory analytical techniques creates an interdisciplinary community capable of maximizing the scientific return from these unique cosmic samples. Educational programs that integrate observational astronomy with laboratory skills will prepare scientists for a future where the study of cosmic materials becomes as important as telescopic observations for understanding planetary formation and galactic evolution. The long-term perspective required for interstellar object research encourages scientific thinking that operates on timescales comparable to geological and astronomical processes, rather than the abbreviated cycles that characterize much contemporary research. This temporal perspective fosters appreciation for the vast scales of cosmic evolution, while encouraging research programs that build knowledge systematically over decades rather than seeking immediate results. Perhaps most remarkably, the study of interstellar visitors reveals that the universe actively participates in scientific research by conducting natural experiments in planetary formation throughout the galaxy and delivering the results to any civilization sophisticated enough to recognize and analyze these cosmic gifts. The galaxy operates as a vast laboratory where stellar evolution, planetary formation, and chemical processing occur under every conceivable combination of physical conditions, while natural selection preserves and transports the most interesting results across interstellar distances for eventual discovery by patient observers. The recognition that we exist within a galaxy that spontaneously shares samples of its cosmic experiments transforms humanity's relationship with the universe from passive observers of distant phenomena to active participants in a galactic-scale scientific enterprise that has been operating for billions of years before our arrival and will continue long after our civilization has passed into cosmic history. Each interstellar visitor represents both a gift from the deep galaxy and an invitation to participate more fully in the ongoing scientific investigation of cosmic evolution that connects all worlds within the vast community of stellar systems that populate our galactic neighborhood. The quiet revolution proceeds one visitor at a time, building understanding through patient accumulation of evidence while revealing the profound truth that we live within a universe far more generous and interconnected than previous generations could have imagined. The messages written in stone and ice continue arriving from the depths of space, carrying news from alien worlds across the darkness between stars to any civilization wise enough to read the stories they tell in the universal language of chemistry and physics. The revolution unfolds in silence and darkness, transforming astronomy one ancient fragment at a time. The darkness between stars no longer seems empty now that we know it carries countless wandering fragments from worlds that formed around other suns. These ancient messengers tumble through the cold vacuum with mechanical patience, their surfaces darkened by millions of years of cosmic radiation, while their interiors preserve the chemical fingerprints of alien planetary formation. Some began their journeys when the galaxy itself was younger, ejected from stellar systems that have long since evolved beyond recognition. Oumuamua fades beyond the reach of telescopes, its mysterious acceleration carrying it back toward the constellation Pegasus, along a trajectory that will take it past other stellar systems over the coming millennia. Somewhere in the deep future, it may encounter gravitational fields strong enough to alter its path, perhaps even capturing it temporarily into orbit around another star where different observers might wonder about its origin and the processes that shaped its unusual elongated form. Borisov continues its own patient journey, its cometary tail now dissipated as solar heating diminishes with distance. The water vapor and organic compounds that streamed from its nucleus have dispersed into the solar wind, carrying traces of alien chemistry into the vast spaces where they will eventually become part of the interstellar medium. In millions of years, these molecules might condense onto dust grains or accumulate in the atmospheres of distant worlds, continuing their cosmic circulation. 3I/Atlas follows its calculated trajectory with the precision that confirms our understanding of celestial mechanics, even while preserving within its composition the secrets of formation around another star. Its surface bears the accumulated signatures of interstellar weathering, cosmic ray bombardment, and the patient chemical processes that operate in the near absolute zero of deep space. These modifications will continue throughout its journey, gradually altering its properties while preserving the deeper signatures of its alien origin. The next visitors are already approaching. Invisible against the stellar background, but detectable to telescopes that now know how to recognize their distinctive motion. Each will carry its own unique story of formation, ejection, and the long journey through galactic space. Some may surprise astronomers with unexpected properties or behaviors that challenge current understanding, while others will confirm theoretical predictions about the diversity of materials produced by planetary formation throughout the galaxy. The sky surveys continue their patient vigil, automated systems scanning the heavens each clear night for the telltale signatures of interstellar motion. The algorithms improve with each detection, learning to recognize subtle patterns that distinguish true visitors from instrumental artifacts and solar system objects with unusual orbits. The databases grow larger, the statistical patterns become clearer, and our understanding of the galactic population of wandering objects slowly solidifies. In the quiet hours before dawn, when the latest observations are processed and new discoveries await confirmation, the universe continues its ancient practice of sharing samples between stellar systems. The messages written in stone and ice drift through the darkness, carrying information across distances and timescales that dwarf human civilization while patiently awaiting the next encounter with observers capable of reading the stories they preserve. The revolution proceeds in silence, transforming our understanding of cosmic evolution one visitor at a time. The galaxy shares its secrets with characteristic patience, delivering its gifts to any civilization that develops the wisdom to recognize their significance and the dedication to decode their messages. The conversation between worlds continues across the vast darkness, written in the universal language of chemistry and physics, preserved in fragments that remember their origins while traveling toward unknown destinations among the stars. Sleep comes easily, knowing that we exist within a universe more generous and interconnected than our ancestors imagined, where ancient materials from alien worlds arrive regularly at our doorstep like letters from distant friends, carrying news of cosmic evolution and planetary formation from throughout the galaxy's long and continuing history of world building among the stars.